Let's give him 1 more minute. Okay, good morning, everyone. Welcome to the first session of the day on controls and dynamics. My name is Yannis Kandaros. I'm a professor at Washington University in St. Louis, and I'm co-chairing this session with Zach Manchester from MIT. We have several exciting talks lined up this morning, so let's get things started. So the first presentation is by Dong-Hoo Kim, presenting fast and stable off-policy reinforcement learning for high-dimensional robot control.
Okay. Hello, everyone. My name is Dong-Hoo Kim from Holiday Robotics, and I'm happy to introduce FlashSAC, a fast and stable off-policy RL for high-dimensional robot control. Our goal in this work is to make soft vector critic, or SAC, just as compelling as PPO. PPO has been the de facto standard in robot learning, as it's often stable and easy to tune. But their problem is that, well, their fundamental problem is that they discard data after a few steps of training. This may not be a problem for low-dimensional tasks, but as we scale up to higher dimensional tasks like humanoids or dexterous hand, reusing past data becomes a necessity. This means that we actually want to use off-policy RL, but their problem is that they are notoriously slow and unstable. So now our goal gets decomposed into two problems: slow learning and unstable learning. Prior works like FastTD3 have addressed slow learning, but did little for stability. Other works like Simba version 2 or XQC focused entirely on stability only. In FlashSAC, we work on combining both directions together to make both fast and stable. Now let's get into the details. So first of all, why is SAC slow? Well, they traditionally used small data with high replay ratio because they primarily focused on sample efficient setting. So to make this more compute efficient, we took lessons from the scaling loss of the supervised learning, which means use more data and larger model and less update steps. And that leads to those specific design choices on the screen, which may seem weak compared to like LLMs or VLAs. But in terms of from-scratch RL field, this is actually a huge leap, and we actually show that scaling past those values is a trade-off. Next, SAC is unstable because the off-policy data exacerbates Bellman bootstrap error, and this kind of error spreads to other state and action pairs due to self-bootstrapping. In response, prior works have shown that we can stabilize the learning dynamics by constraining the feature, gradient, and weight norms. And just to name a few, we apply batch norm for the features, weight normalization for the weights, and distributional critic to stabilize the gradients. And here are some ablation experiments. And finally, we evaluate the resulting FlashSAC on more than 60 tasks across 10 simulators, including Isaac Lab, Musical Playground, and Genesis, etc. Here, we aggregate 15 low-dimensional tasks, including Franca Arm on the top row. And on the bottom row, we aggregate 10 high-dimensional tasks, including Shadow Hands or Booster T1. And as mentioned in the introduction, PPO performs quite well in low-dimensional tasks, but the gap widens as we move on to higher-dimensional ones. On the other hand, FlashSAC performs consistently well in both regimes, outperforming PPO and a very strong off-policy baseline FastTD3 within just a fraction of time. Finally, we show the zero-shot sim-to-real capability of FlashSAC using a Unitree G1 humanoid doing a blind locomotion. Using a single RTX 5090 GPU, FlashSAC learns omnidirectional movement in just about 20 minutes, and in rough terrains, it learns to climb real stairs using 4 hours, while PPO takes 20. So to summarize, FlashSAC is simply fast and stable off-policy RL that beats PPO within just a fraction of time. So if you're using PPO for any form of robot learning, please give FlashSAC a try. Thank you for listening, and I'm happy to discuss in the poster session.
Next, we have J.J. Lee presenting Realizing Robotic Swimming with Unified Fluid Robot Multiphysics.
So in this age of humanoids and VLAs, people ask me, why should we care about swimming? And I point them at this, which is, if you looked at fish, you probably realize that they're really good swimmers, much better than us humans. But if we look at our robotic counterparts, they're typically slow and clunky, and they're made for these long oceanographic surveys, but it still presents the question, if fish really are so much more maneuverable and agile and efficient, why aren't robots swimming the same way? So one of the modeling challenges that we looked at was in the dynamics modeling, which was the fluid structure interaction problem, which is a well-studied problem for decades by the aerospace and hydrodynamics community with a big emphasis on accurate flow physics. And in recent years, we started seeing these multi-purpose robotic simulators pop up that provide particle-based fluid models for really good visual rendering. And in this work, we tried to take these high-fidelity CFD models and combine them with features that we care about in robotics. So kind of to start looking at this, we start with our incompressible Navier-Stokes equations, which is terrifying, and as well as the manipulator equation for our robots that we're familiar with. But this presents a problem, which is how do I take this nonlinear PDE with its Laplacians and nablas and complex convective terms and combine it with the ODE that models our robot? And the way we usually do this was ad hoc, heuristically coupling forces, but if we actually use variational calculus to look one level deeper, we see that there's actually this unifying optimization problem that brings these two very distinct principles together, where the constraints actually provide the coupling of these two distinct physics. And the dual variable associated with them actually maps the forces that we see in these differential equations. So this is a nice theoretical nugget. So we asked ourselves, if this unifying least action principle is really what brings physics together, why not discretize that problem directly? And we did this to realize the swimming of an EO robot that we validated on hardware. And the first case that we looked at was this undulatory steady swimming motion, where we see that in our unified approach, we're able to actually model the motion that we see on hardware. Meanwhile, the particle-based representation in Genesis isn't able to do so. Not to say that Genesis is poorly implemented, it's just we believe that this particle-based representation isn't the right one. But the simulator has to be useful for robotics, so we looked at using the simulator to optimize what's called a C-start, which is a predator evasion technique used by fish to achieve rapid acceleration and quick change of direction. And we posed this trajectory optimization problem as optimizing a parameterized gate, where we try to take the final configuration and steer it towards a goal one. And we did it with a quadratic objective, where our unified approach provides the dynamics constraint that we differentiate through. So we start off with this initial guess of a swimmer going forwards, and we're able to optimize it to achieve a 90-degree turn. And what's really remarkable is that we're actually able to see the open hoop rollout match really well on hardware, while Genesis continues to struggle. So there's still a lot of future work left. So one of the things we're looking at is to extend this to 3D while maintaining computational feasibility. Another one is actually simulating pressure sensors for reduced order output feedback control. And another one is design optimization, where if we have a passive swimmer behind like a vortex wake, how do we optimize the shape to get it to passively swim forwards? But those are a lot, but the main takeaway being that multi-physics isn't really a thing. There's really just one physics, and maybe we should start trying to develop simulators around that instead.
The next presentation is grounding discrete time joint level acceleration bounds in voltage constrained actuation by Lingwei Zhang.
Hello everyone, my name is Lingwei Zhang from CHK. Today I will present VRA, the voltage realizable acceleration. Let's start with the two less dance jump. We impose kinematic constraints to the select joints to test the motion near the boundaries. Please note that the whole body controllers does not know the constraints. Only the joint level controllers know the constraints, and the whole body controllers are unmodified. And here are the results. And you can see the standard methods fail during near the position limits, while VRA helps the same whole body controllers finish the task while respecting the drawing limits. So VRA helps to realize the drawing level kinematic constraints. So why does the standard method fails if the command is kinematically feasible? To isolate the cause, we remove the contact and coupling in a single motor test. We designed to expose the mismatch clearly, and we deliberately drive it to the extreme condition to near its boundaries. And we use a viability-based control, namely VBAC. It computes the acceleration bounds from the kinematic constraints and such as velocity and position. And you can see, even if the command is kinematically feasible, the motor chatters and fails to stop. So the kinematic realizability is not equal to the actuation realization. So our idea is very simple and intuitive. We just propose VRA to make the acceleration both kinematically feasible and the actuation realizable. Existing methods assume a constant acceleration bounds and compute and input it to the kinematic filter. And torque controller convert the kinematic reasoning to torque and use the static motor region to clip it after the command is chosen. This is too late because it will cause torque distortion and unrealizable acceleration near the bounds. So VRA makes two changes. We replace the static motor region with a state-dependent motor actuator model so we can get a realizable acceleration and then send it back to the kinematic filter. So the filter is less conservative, and the final command is both kinematic feasible and actuator realizable. Now let's see how we get these bounds. For the QDD and PMS and FOC-based actuators, the joint acceleration is depending on the torque, and torque depends on the current. So given any joint speed, the voltage limits determine which currents are realizable. So if we have a realizable voltage, then we can get a realizable current, and then we can get the realizable torque, and finally we can get the realizable acceleration. So the essence of VERA is to convert the motor physics into the voltage realizable acceleration set. So the final output is both kinematic feasible and realizable actuators. We carry out extensive experiments. Please refer to our paper for more details. Here, I choose one representative experiment here, and you can see the VERA can keep the motion stable while the VBAC causes chattering or fail in the task. And among these tests, VRA keeps less oscillation, less conservation, and no limit violation. And it can be plugged into many controllers, such as CBF and whole body controllers. So takeaway, the VRA is a missing interface between the controllers and the hardwares. It can be plugged into many controllers, and please scan the QR code for our code's open source hardwares and PCB files. You can try the VRA in your laboratory or home. Thank you for your listening.
The next presentation is GPU-accelerated nonlinear robust trajectory optimization presented by Jiawei Wang.
Good morning, RSS. This is Joe from UC San Diego and Georgia Tech. Today, I'll talk about CU and RTO. The main goal is simple. We want robust planning to be much faster, while keep safety guarantees under abundant disturbances. Let me first briefly explain what an RTO does. So first, I would like to shout out to my first author, Shea, who originally proposed this framework. At a high level, an RTO optimizes a fan disturbances policy. And instead of only planning a normal control sequence, it also optimizes feedback gains that react to disturbances. Inside each outer iteration, there is an ADMM inner loop that updates the feedback gains, feed-forward controls, and the door updates. This gives us a robust controller, but it also makes the solver computationally expensive. The main bottleneck is the feedback gain update. The block contains a large number of SLC constraints coming from robust reformulation, which takes about 95% of the total runtime. So the key here is to accelerate this projection-heavy step on GPU. Our first version is an RTL-DR. Here, we make a minimal change to its original solver. We replace the SOCP support solver with Douglas range 4 splitting. The nice thing is the core projections are independent across constraints. And each projection has a closed-form solution, which is a very neutral fate for GPU. But the DR has some CPU-GPU communication, which is very heavy. And it also introduces extra DR loop. So we take one step further. We reformulate the inner problem. So the SOC projections are integrated directly into the ADMM loop. And then we run the full ADMM loop on GPU. The CPU still handles outer successive linearization. But once the constraints are formed, we upload them to GPU once per outer iteration. After that, the inner loop stays on the device. By keeping the whole loop on the GPU, we avoid repeat synchronization and get better scaling. So we evaluate the framework on 3 simulation systems for the unicycle. Great. For the unicycle, the NRTL for ADMM maintains 100% constraint satisfaction, while achieving about 21 times speedup. Across the broader sweeps of uncertainty and number of obstacles, speedup could be up to 160 times. For the quadcopter, we again get 100% constraint satisfaction with about 31 times speedup in the demo case. We also test on a Franken manipulator, which shows that framework can scale to higher dimension systems with second-order dynamics. So finally, we test the method on a real differential drive robot with normal control only. The check-in error builds up, and the robot does not reliably reach to the goal region. But with CU and RTO, the robot can compensate for real-world model mismatch and reach the goal much more reliably. So this work is a two-team effort, and I would like to give huge thanks to my co-author Ashia and Professor Theodoro from Georgia Tech. Also, please scan the QR code. There is an interactive demo. You can create your own planning problem and say how fast GPU accelerated structure optimization could be. Welcome to the era of GPU accelerated optimization. Thank you.
Next, we have Jeffrey Fung presenting safe, large-scale, robust, nonlinear MPC in milliseconds via reachability-constrained system-level synthesis on the GPU.
Hello, everyone. I'll be presenting our work on installing robust control for high-dimensional systems on their GPU. Robust real-time control remains a major challenge for modern robotics as you plan over high-dimensional systems with hundreds of states over long planning horizons. Classical verification methods provide strong formal guarantees, but scale poorly to higher dimensional systems. On the other hand, data-driven methods scale well due to the use of massive offline compute, but sacrifice the formal guarantees we so desire. This leaves a gap between safety and scalability, and our goal is to close this gap. We consider a nonlinear system subject to bounded disturbances, and we want to compute a nominal trajectory that reaches the goal, and a robust feedback controller that provides us a safety certificate for all constraints, and ensures we remain safe for all disturbances. To solve this efficiently, we do system-level synthesis on the GPU. System-level synthesis, or SLS, is an iterative procedure where we first calculate a nominal trajectory using sequential Riccati recursions. We then compute a robust feedback controller, again using these sequential Riccati recursions, that optimize the propagation of disturbances injected at each time step along the horizon. Each of these propagated disturbances are then accumulated to form our forward reachable tubes. And lastly, we use these forward reachable tubes to tighten our constraints to ensure robust constraint satisfaction. However, existing approaches to SLS suffer computationally as they rely on these sequential operations that must be computed one step at a time. As the planning horizon and state dimension grow, these serial computations increasingly become bottleneck. Our contribution is to remove these serial dependencies by using structure exploring parallelization on the GPU, enabling the entire pipeline to run efficiently on the GPU. Our method uses two key mechanisms, parallel associative scans and parallel matrix operations. Given a set of elements and an associative operator, a parallel associative scan calculates their prefix sums in logarithmic time. What this basically allows us to do is to reformulate this sequential operation into a parallel reduction tree, reducing the complexity from linear to logarithmic. This reduction in computation time is the key enabler of our method's scalability compared to previous state-of-the-art methods. Using these two mechanisms, we accelerate every major stage of the SLS pipeline. Because the Riccati recursions are associative, we reformulate them as parallel associative scans, enabling the trajectory generation and robust controller synthesis to run in logarithmic time. Using the robust controller, we then evaluate our disturbance propagations all in parallel, allowing for the forward reachable sets to also be calculated in logarithmic time. This end-to-end GPU pipeline removes all CPU bottlenecks and enables our method to scale well to high-dimensional systems and long horizons. We first compare our method against deep reach, which is a learning-based reachability approach. In the obstacle avoidance tasks, deep reach fails to certify the entire trajectory, colliding with the obstacle in around 20% of experiments, which demonstrates the limitations of learning-based reachability. In contrast, our method uses the forward reachable tubes to certify the trajectory, remaining 100% safety. Across long planning horizons, we show our method being able to calculate policies under multiple constraints and extended task horizons. Furthermore, we demonstrate the logarithmic scaling of our method, showing a 230 times improvements over the previous state-of-the-art method. On physical hardware, on a 61-dimensional quadruped, we run our approach online in a real-time iteration scheme with solve times averaging around 20 milliseconds. On a 75-dimensional humanoid system, we show the humanoid robustly navigating through these two gates with solve times around 25 milliseconds, showing the practicality of our method for high-dimensional systems. In summary, we combine reachability analysis, robust controller synthesis, and non-trajectory generation into a unified GPU framework for robust control for high-dimensional systems. Thank you.
The next talk is Bellman value decomposition for task logic in safe optimal control by William Sharpless.
Hi, how's it going? This is our work on Bellman value decomposition for task logic. Real-world tasks involve nuanced goal and safety specs. Consider, for example, a herding task for a drone quadruped team, or a delivery task for a similar team that needs to resupply and deliver packages iteratively. To solve these problems, many approaches exist, but these problems are inherently challenging. Classic control is limited by high-dimensional nonlinearity. Standard RL or an MPC requires expensive tuning and suffers from misalignment. And imitation is inaccessible when no solution data exists. In this work, we propose to solve the optimal value for a formalized task. However, the corresponding Bellman equation is difficult and has impeded this paradigm. To overcome this, we introduce an algebra for decomposing the value into a graph of values, and next introduced VDPPO to embed the decomposition and bootstrap the graph to solve it simultaneously. Ultimately, this yields highly performant policies for these tasks that can scale but do not need to. For decomposition, we present the VDR, an algebra for distributing optimal actions across the payoff of current logic and logic to go in a macro-scale dynamic programming manner. This allows us to solve multi-achievement and multi-recurrence problems exactly. For example, consider a task to reach two goals and avoid walls. The optimal value for this task can be decomposed, i.e. rewritten, yielding a value defined by child values corresponding to pieces of the overall logic. And this process can be recursed until reaching the leaf or tail task of avoiding the wall indefinitely. The original value reduces to a graph of HJ values, each with a known Bellman equation is the point. Once a task is parsed and the value graph synthesized with the software we wrote, the graph can be embedded into a single actor and critic for efficiency and allows you to reuse learned behaviors. For each node, VDPPO is rolling out trajectories with the corresponding policy embedding simultaneously across nodes and updates the value embedding with the corresponding Bellman backup, where you're then bootstrapping the implicit dependencies for children. At test time, the policy begins at the root node and switches down the graph as predicates are satisfied. We test VDPPO in simulation on tasks with scaled logic and also in scaled dimension and find it outperforms all methods. Lastly, we test VDPPO on these two problems from before, and here I'll show the herding video, but see the site for the delivery as well. So here, the herd is on the left, they're all drones, and we have the herder team on the right, which is a quadruped and a drone. One is modeled to be slower. We'd like the herd to move through this narrow gap and then ultimately be stabilized in this lower right-hand region. You're watching the emergent solution here, which I should say first, the herd drones are moving with a passive sort of Gaussian policy, which tells them to move away from whatever's nearest. And here you're seeing that we naturally emerge this solution where the fast agent, the drone, will move across the wall while the slow agent will support and act to keep the herd together until it ultimately traverses to the lower right-hand corner. We test this with a variety of initial conditions of herd distributions, and in all these cases you can see the learned solution is to have this fast agent move across the gap while the slow agent acts as support to contain it in these regions as it moves along. Ultimately, we propose that the success here is because of the structuring of this problem, which is structure that is learned and therefore does not impede the process itself. Ultimately, you can ask me more questions at our poster if you'd like. I'd be happy to take them now as well. Thank you so much.
Great. The next talk is closing the sim-to-real gap via friction-aware reinforcement learning for underactuated spherical dynamics, presented by Chao-Yang Song.
A ball balancing robot, also known as a ballbot, is a dynamic stable mobile system designed to balance on a single spherical wheel. Adding payloads on top enables a wide range of applications that call for agile movement in human environments in omnidirections without turning. And the humanoid robot is one that adds a humanoid torso on top, making it a unique design with growing interest. Designed with cost-effective robustness, learning under-actuated spherical dynamics, and interaction with a user-friendly interface are the research gaps that motivated this research. As RoboLay is basically designed by subtractive reconfiguration using core components from a quadruped that we developed earlier with newly introduced structural parts we designed specifically for as RoboLay. Also inherited from the quadruped are the AdsMagic app with an iPhone Pro for multimodal perception at a low cost, and the AdsBrain box for battery-powered robot control with an IMU. With RoboLay, we propose a learning-based approach to address the underactuated spherical dynamics with Omni wheels. Three motors of similar torque rating and size are used to drive the Omni wheels. Each provides 2 to 5 times more torque than previous designs, but also about 20 times cheaper. And modeling the physics and geometry of each Omni wheel and its 12 rollers is critically important, capturing the lateral compliance for learning the underactuated contact dynamics. We model the spherical wheel as a virtual low-damped ball joint with a torso, which turned out to be sufficiently robust, directly transferable to simulations and real-world hardware tests. We defined 2 reinforcement learning tasks, including one for velocity tracking and another for stationary keeping. We found that LQR controller degrades rapidly when nominal assumptions are violated, whereas RL controllers preserves the performance with satisfactory outcomes. And our reward shaping mainly affects the tracking holding trade-off, and the exponential tracking reward achieves the best tracking accuracy overall. Removing the domain recommendation significantly reduces robustness, highlighting the essential role of realistic sensing and contact perturbation for reliable generalization. As a result, we are glad to share the first deployment of end-to-end reinforcement learning on a humanoid ballbot using zero-shot sim-to-real transfer across various floor textures in both indoor and outdoor conditions. In addition, as RoboLay also generalizes well in new conditions, successfully moved down a 5-degree slope on an office carpet and overcame a slight aluminum bump on the door frame and then transitioned on a hard and anti-slip floor. Further hardware development tests show promising and capable performance, validating our sim-to-real method with as RoboLay. Yes. Okay. So with our future research, we aim to pave the path towards crowdsourcing human data collected from consumer-grade mobile devices and a cost-effective hardware system for graceful retargeting. Here are some of our recent developments, and if interested, you can scan the QR code to try with the app. And here concludes our work in Agrawal, and thank you for your attention.
All right, our next talk is stabilizing 3D continuum arm rollouts via equilibrium anchoring and feature-lifted residual learning, presented by Asan Tanvir, who unfortunately couldn't be here, so we're going to see a recording.
Introduces an equilibrium-anchored residual learning framework for stabilizing open-loop multi-step predictions of a three-dimensional continuum arm under actuation distribution shift. Continuum robots are highly dexterous, but their compliance makes multi-step prediction difficult. This comparison shows the core problem under actuation distribution shift. The equilibrium prior, shown in blue, remains stable, but exhibits large steady-state error. The residual predictor, in orange, captures transient motion, but drifts and can become unphysical. Naively combining these two ideas does not, by itself, solve the problem, which is the focus of this work. Prior residual physics and residual Koopman methods typically add a learned correction to a fixed one-step model. Our approach is different. It explicitly separates two roles within the rollout itself. At every single step, a contractive update re-anchors the prediction toward the equilibrium manifold before the residual is applied, not as a one-time correction, but as a recurring stabilizing force throughout the rollout. The residual is then trained specifically on these anchored states, so it learns only the transient dynamics consistent with what the anchor produces. The framework relies on two datasets with distinct roles. An inexpensive equilibrium dataset of static input pose pairs is used to learn the actuation conditioned equilibrium map. A separate dynamic trajectory dataset provides the one-step transitions used to learn the residual. This separation is what allows the steady state and transient components to be learned independently, then composed through the anchored update. The equilibrium map P of U is learned by ridge regression on the static dataset. At each rollout step, the contractive anchor update blends the current predicted state toward this equilibrium estimate, controlled by a scalar beta. A formal stability analysis shows this update bounds the rollout, and under a mild Lipschitz condition on the residual, the full recursion is exponentially stable. The residual correction is learned from the dynamic dataset using a feature-lifted linear in parameters model. Critically, it is trained on the anchored states produced by the equilibrium update, not on raw trajectory states, matching exactly what the model encounters during open loop rollout. This prior consistent training is what allows the residual to recover transient dynamics without reintroducing the drift the anchor was designed to suppress. So how does the hybrid model perform? On 200-step rollouts under actuation shift, larger amplitudes and higher dominant frequencies than training. The hybrid reduces backbone position error by 26% and tip error by 27% relative to the anchor alone, while remaining stable across all 19 test trajectories. The residual-only predictor achieves comparable accuracy when stable, but diverges on several trajectories, visible in these backbone snapshots where the predicted shape grows to an unphysical length. And the equilibrium anchor needs very little data. Just 10% of the static dataset is enough to match full performance. And these gains are not limited to simulation only. On a pneumatic soft-tail robot tested under actuation frequency shift, hybrid reduces error by at least 51% versus the anchor and 74% versus the residual. And on the Van der Pol and pendulum cart benchmarks, hybrid achieves 0 catastrophic rollout failures, while a competing residual Koopman baseline diverges on up to 4% of trials. Taken together, these results point to a simple guideline. Maintaining an explicit steady-state reference during recursive prediction can be as important as improving one-step accuracy.
Okay. All right. Next, we'll hear from Jia Liu presenting learning-based adaptive control for surgical robotic exposure tasks on deformable tissues.
Hi everyone, I'm Jiayi Liu from Harvard University of Science and Technology. In this paper, we present a learning-based adaptive control method for surgical tissue retraction. In many surgeries, tissue retraction is a common subtask that helps the surgeon assess a region of interest. For example, during a gallbladder removal, the liver needs to be pulled back to expose the gallbladder. However, making this autonomous with surgical robots comes with some challenges, such as irregular tissue boundaries, nonlinear deformation, and limited perception. In response, we formulate it as a visual exposure task. The target region is completely or partially covered by the tissue. The robot grasps the tissue boundary and uses only camera feedback to decide its set of movements, continuously adjusting until the target is fully exposed. To achieve this, we propose a learning-based adaptive control framework. First, we build a simulation with deformable tissues and target markers to collect training data. We use the data to train a deep model that can predict both the boundary shape and the retracting force for any given robot action. Then we use the trained model to initialize the deformation Jacobian. It acts as a great starting guide for the estimator and controller. After that, this Jacobian is fed into our closed-loop controller to calculate the robot's next move. Crucially, the Jacobian is updated online step by step using the visual feedback. At the same time, the force prediction forms a safety constraint within the controller. Additionally, even before the retraction starts, we combine the model with a genetic algorithm to find the optimal grasping point, making the entire process safe and efficient from the very beginning. We validate our method in simulation and on real-world tissues like sponges and porcine livers. First, we tested the deformation prediction accuracy of the trained model. The porcine liver is the most challenging case because of its complex biomechanics. But even with a 10 centimeter retraction, the mean shape error stays below 1 centimeter, accurately capturing the deformation chains. Second, we ran the complete retraction pipeline from grasping point selection all the way to full exposure. In the real-world tests, we used the segment anything mode to extract the tissue boundaries. To make it usable for closed-loop control, we then applied basis function fitting to project it into a low-dimensional parameter space. For more setups, the success rate is nearly 100%. However, in extreme cases, the force limit safely stops the robot before full exposure to prevent tissue damage. Finally, we evaluated our grasping point optimization. We uniformly sampled several candidate points along the tissue boundary. The results show that our optimized grasping points require lower retraction forces, greatly reducing the risk. Okay, for more information, please check out the link on the screen. Thank you for your attention, and see you at the poster.
All right, next, Fabian Schramm will present variance-reduced MPPI via quadratic model approximation.
Hi, I'm Fabian Schramm from INRIA in Paris, and I present variance-reduced MPPI via quadratic model approximation. MPPI is a popular sampling-based controller, derivative-free, handles non-smooth cost like contact, and parallelizes on GPU. But it samples from an isotropic Gaussian that ignores the cost geometry. The result is high estimator variance and weight degeneracy. So vanilla MPPI often needs thousands of rollouts to be stable, which is impractical under real-time or low sample budgets. So our question is, can we keep this flexibility but converge faster with far fewer samples? We start from the Boltzmann update, which reweights the prior by the cost f. Our key insight is that to decompose the objective into a known model mk plus a residual rk. This factorizes the optimal distribution into a model-guided prior times a residual reweighting. This factorization is valid for any model. We therefore sample from an informed prior and weight only by the residual. The gains come from choosing a model that actually captures useful geometry, which leads to a small residual and lower variance. To make this tractable, we choose a quadratic model around the current mean using a gradient and a Hessian. As the guided prior is still Gaussian, we can compute the mean and covariance of the guided prior in closed form. The algorithm is simple. Build the model, form the guided prior analytically, sample from it, and update with residual weights. The analytical shift injects the geometry, and sampling only has to explore the residual around the new center. Crucially, the framework is agnostic to where the curvature comes from. You plug in any quadratic model into the same closed form update. If you have exact derivatives, use them. For least square cost, use a Gauss-Newton Hessian. And with only gradients, use BFGS. And when the cost is own black box or non-smooth, you can estimate gradient and Hessian purely from function evaluations using randomized smoothing, or you can learn it. To the results. Back on that toy example 2D Valley. With the same 100 samples, vanilla MPPI collapses to an effective sampling size of 1, which is severe degeneracy, while ours, with the same hyperparameters, stays above 23 and approaches the optimum much faster. And on standard benchmarks, we converge in fewer iterations and with lower variance than vanilla MPPI and CMAES. On the card pull task, the dynamics are differentiated automatically through Pinocchio and Casadi. This is the ideal model case, just like in the static benchmarks. Sweeping the sampling budget from 1,000 down to only 2, the baselines degrade badly with fewer samples, while ours is able to solve it with as few as 2 samples, thanks to the model. We then ask, how does this degrade once the model is only approximate? Gauss-Newton and BFGS still track the exact Hessian performance closely, and only the diagonal Adam approximation lags, but all of them still beat vanilla. As a final step, we used randomized smoothing on a controlled but contact-rich manipulation task with non-smooth dynamics in Mujoku. Across 200 random problems, our method converges more reliable than the baselines. So to summarize, a model residual decomposition gives variance reduction and a closed-form Newton-like step at the distribution level. The main trade-off is model construction cost. Thank you, and I'm happy to see you at the poster session.
All right, next, Heng Yang will present tempered sequential Monte Carlo for trajectory and policy optimization with differentiable dynamics.
Hi everyone, I'm Heng Yang from Harvard. Today I'll present tempered sequential Monte Carlo for trajectory and policy optimization with differentiable dynamics. The problem we study is trajectory and policy optimization. We have a discrete time dynamical system, a trajectory cost over a finite horizon t, and a controller parameterized by theta. This formulation covers 2 common settings. In trajectory optimization, the initial state is fixed and theta is an open loop control sequence. In policy optimization, the initial state comes from a distribution and theta parameterizes a feedback policy, for example, using a neural network. Our motivation comes from differentiable dynamics. Differentiable simulators, differentiable contact models, and learned world models let us compute gradients through trajectory rollouts. Gradient-based methods exploit this structure and converge quickly locally, but they can get trapped in poor local minima. Sampling-based methods explore more globally, but often converge slowly. The goal is therefore to combine these 2 advantages in one principled algorithm. The first idea is to view control design as inference. Instead of optimizing one controller parameter theta, we optimize the distribution p over theta, regularized towards a prior p0. This gives a closed-form optimal distribution, the prior p0 tilted by the negative trajectory energy. Low-cost controllers are exponentially upweighted. The challenge is that at low temperature, this distribution becomes sharp, multimodal, and difficult to sample. To address this, we use tempered sequential Monte Carlo. TSMC constructs a tempering path from the easy prior distribution to the difficult target distribution. As beta increases from 0 to 1, the energy landscape gradually changes from a simple prior-dominated landscape to the original non-convex control objective. At each tempering level, TSMC represents a current distribution with weighted particles. First, important sampling reweights particles according to their trajectory energy. Then the next temperature is chosen adaptively using effective sample size, so the weights do not collapse too quickly. Finally, after resampling, Hamiltonian Monte Carlo rejuvenates the particles. This is where differentiability enters the place. HMC uses exact gradients of the trajectory energy to move particles efficiently while preserving the current temper distribution. For trajectory validation, TSMC applies directly. The energy is just the cost of one trajectory rollout, and its gradient can be computed exactly by the adjoint method or automatic differentiation. For policy optimization, the energy is an expectation over initial states, so we use two practical variants. One fixes a batch of initial states to form a deterministic approximation. The other runs TSMC in an extended space where each particle also carries sampled initial states. For trajectory validation, we compare against several baselines, NUS without tempering, MALA, MPPI, and IPOPT from multiple initializations. All methods use the same initial particles. On the simple inverted pendulum, most methods work very well, but on the harder Acrobot and pusher-slider problems, TSMC achieves substantially lower trajectory cost, showing the benefit of combining tempering with gradient-based particle moves. Here are rollout visualizations. For Acrobot, TSMC produces a successful swing up, while the baselines remain farther from the upright goal. For pusher-slider, TSMC is also the method that reaches the target poles most reliably. For policy optimization, we compare against PPO and SAC. On sparse reward inverted pendulum, TSMC reaches strong performance. On Acrobot and double pendulum on a cart, the energy landscapes are sharper and more non-convex, but TSMC still trains better neural policies than the RL baselines. To summarize, TSMC turns differentiable control into sampling from a tilted distribution, using sampling for exploration and gradients for efficient local moves. Thank you.
All right, next, Ishan Mahajan will present TinySDP, real-time semi-definite optimization for certifiable and agile edge robotics.
Hey everyone, I'm Ishan, and today I'll be presenting our work on TinySDP. So in robotics, there are plenty of ways to do obstacle avoidance. We have linear constraints that are fast and computationally cheap, control barrier functions or CBFs that encode safety directly inside the controller. And these methods work great in simple open space settings, but often in tight trap-like environments with embedded compute, these methods struggle. For example, consider a deadlock scenario, which is basically U-shaped. Here, the controller needs enough geometric reasoning to get out of the trap-like setting. On the left, linear constraints struggle. Here, obstacle avoidance is enforced through local tangent half-space approximations, and without a margin, the method basically tunnels through the obstacle, resulting in a crash. With the margin, the method does become safe, but often overly conservative, leading to long paths and also getting really far from the goal. On the right, high-order control barrier functions also struggle, but for a different reason. They have a different formulation, but it's still a local reactive method at the end of the day. So we have these two methods that are local and reactive and often struggle, and at the other end of the spectrum, we have semi-definite programming, which has shown to work great for obstacle avoidance and other collision avoidance, because they have the ability to reason about the geometry globally by lifting the constraints. But a major problem with SDPs is they're very, very computationally expensive, mainly because they have to lift the constraints. And so there's this gap. Local methods work great, but are computationally cheap, whereas SDPs have the ability to reason about the geometry globally, but are very, very computationally expensive. And we basically bridge this gap with TinySDP, the first real-time SDP solver inside an embedded control stack. And the way we design the framework is basically we start with ADMM-based model predictive control, which is 3 steps: the primal update that reasons about the cost and the dynamics, the slack update that enforces the projections, and the dual update that makes sure that the primal and the slack variables agree. But a problem with this is the primal update is very, very computationally expensive as it scales cubically with the horizon. So we need to compress this step to get this working on embedded compute. Previous work, like TinyMPC, basically caches certain terms offline and then does this offline-online split. We built on this work and replaced the slack projection highlighted here with a positive semi-definite projection with a positive semi-definite projection. And this gives us our tiny STB algorithm, which is an offline-online split. Offline, we pre-compute the matrix-heavy operations that involve invergence and divergence. And then online, we lift the current state and do this three-step ADMM process. And now returning back to the U-shaped benchmark, tiny STP in blue is successfully able to navigate the trap-like environment while being 15.2 times more precise and producing 30% shorter paths. And then the same framework also extends to other 3D or n-dimensional environments in general, as shown in the sweeping barrier and the rising barrier demos. Finally, we deploy tiny STP onboard a crazy fly at 25 Hertz, where the maneuver is to get to a goal right behind the arm. Tiny STP successfully avoids the moving arm as it comes across its path, while running at 25 Hertz and taking a solve time roughly between 14 to 15 milliseconds. So to summarize, we introduced tiny STP, the first real-time STP solver on board a microcontroller that runs at 25 Hertz, averaging a solve time between 14 to 15 milliseconds and consumes only 1.47 kilobytes of additional static memory. Going forward, we're still exploring how to make tiny STP more robust, which includes more expressive lifts and harder dynamic environments. If you have any questions or want to discuss more about where tiny STP is headed next, I would love to talk. Thank you.
All right, next up is Leonard Renner, high-precision hydraulic excavator control for heavy-duty grading.
Hi, today I will present our work regarding high-precision hydraulic excavator control for heavy-duty grading. As you can see here, the task that we're trying to solve is actually using one of those big hydraulic machines to create a very precise surface while removing a substantial amount of material. The problem with these, with the existing solutions in that field is it actually advancing? Yes. The problem is existing solutions here get deflected. So there's a little bit of compliance in the hydraulics, and those hydraulic joints are actually load dependent. So the controllers that exist get pushed up, and they actually don't use all of the machine. So the machine stalls before the maximum function pressure of the stick joint or of the bucket joint is actually reached. Our system, on the other hand, achieves an accuracy on one of those 24-ton standard excavators of about 1.8 centimeters. On smaller, like 13-ton machines with load sensing hydraulics, we reach about 0.5 centimeters accuracy. Also, with the method that I'll be presenting today, you actually do not stall before the maximum function pressure is reached, but you use all of the machine available. The problem is there's much of different hydraulic models and much of different hydraulic architectures out there that these machines use. The much nicer one to use is actually the load sensing architecture. Load sensing is hydraulically stiff, which means you open a valve and the machine is moving at a constant rate. If we are not stalling the machine will exert maximum pressure. Negative flow control, on the other hand, is a hydraulically soft architecture. So you move up a valve and the speed that the joint is actually moving depends on the back pressure in the hydraulic system. This is due to the interplay between the main control valve and the reference orifice that with the negative flow control system actually steers the flow controlling element, the variable displacement pump that will actually create the power that goes into the hydraulic functions. In our work, we model this negative flow control to actually get accurate control on these systems as well. To be agnostic to those machines, we divert between the path tracking controller, which in the end also just outputs joint velocity commands, and a low-level hydraulic joint velocity controller that is aware of the hydraulics that it's actually working on. We use a calibrated hydraulic model to arbitrate between the load sensing hydraulics, which are hydraulically stiff, and our negative flow control hydraulics, which are then dependent on the cylinder pressure, the back pressure, the joint position, and the accelerations in the system. The MPC controller also compensates for the delay in the system, for the dead time, for the actual kinematic constraints, and optimizes an optimal trajectory to follow the target surface that we would like to grade on. So for the load sensing, which are hydraulically stiff, this hydraulic model is actually quite straightforward. We can calibrate it by just doing experiments in air. We collect the actual velocity that we are getting for the different valve openings. We do a little lookup table, and we are done. We can achieve very high accuracy with those on those machines. On negative flow control, though, we actually have to model what is happening in the main control valve and within the reference orifice. We can calibrate this model by stalling the machine in the ground and actually seeing different load behaviors at different commands. Then we model this, the hydraulic actual setup, and we can convert this into this two-dimensional lookup table, which then gives us a function between the pseudo back pressure, which is inertia compensated, and the actual desired flow that we want to reach to the valve opening that we need to command to the main control valve. By doing this, we can now create different load scenarios, and the different load scenarios are then well tracked in terms of velocity for that joint. And as you can see here, the feed-forward term that we are getting from our calibrated hydraulic model actually varies significantly while we achieve the same velocity on our tracking boom joint. On a load sensing machine, which is, again, much nicer to control, we can actually achieve so high accuracy that we can comfortably open a bottle of beer. Thank you very much, and I'm looking forward to discussing this at the paper session.
Okay, now we're going to have some Q&A time, so we'd like to ask all the speakers to come back up with the microphones, and then in the audience, feel free to come up to the microphones. Questions? All right, looks like we have a question over here.
Hi. I've got a question for the multi-physics paper. Yeah, so that was really cool. If I've understood it correctly, you've got a Lagrangian, basically. And I guess when you work out the Euler-Lagrange equations, you'll recover the Navier-Stokes and the joint equations. So how does that actually help you simulate a system? Because you still have to end up solving the ODEs and the PDE.
So yeah, so what we do is we actually use what's called discrete variational mechanics. So you're right, you have to write down the Lagrangians and all that stuff for the physics. But kind of the idea is that I can, instead of discretizing the ODEs, I discretize the least action principle using quadrature. And if you do essentially crank the mass and derive the first order necessary equations, what you get is the discrete time schemes for the ODE and PDE combined. And really the nice part here is that the coupling is implicitly derived from that. So usually how we usually solve these multi-physics problems that I have a CFD package, I have my robot dynamics package, I have to somehow couple the forces, and they're usually very ad hoc, heuristic-y. But in this case, because you're thinking about the physics, both physics together, that coupling is implicitly derived, and you kind of get it without having to think about how to set that up. So it's strongly coupled versus weakly coupled.
Cool, thank you. I'll come chat to you more during the poster session.
Jeanette?
Hey. I have a question for CU NRTO. Yeah, thank you for the nice talk. I was wondering if, as a robotics practitioner, I want like a really fast motion planning method, and you have a specific trajectory optimization method kind of in the back end and sped that up. But I wonder if you can help me like understand a little bit the landscape. When do I pick your sped up method over maybe other solutions that are out there?
Sounds good. Thank you. That's a great question. So there's also a lot of work that's working on the GPU-accelerated traditional optimization algorithms. So I think the main thing here, what we do is we accelerate an algorithm called NRTO, which is proposed, I think, this year as well, from my co-first author. So NRTO mainly focuses on the problems that need robustness guarantees. So, for example, like when in some strict scenarios, we need 100% constant satisfaction in any cases. And NRTO is designed for those kind of problems that you require strict guarantees. And traditionally, like the NRTO will take about probably, like for some hard problems in our experiment, it will take about almost 1 week to solve a single trajectory. But with a GPU accelerated approach, we reduce that to minute level. So make the NRTO actually feasible in the real world scenarios. So that's our focus. So we are solving a different problem, I would say.
Thank you.
Thank you.
Okay, it looks like we have a question in the back there.
There's a question for Ishan for Tiny MPC. So if the relaxation is loose, are you still able to sort of glean any information from it? Is there like a rounding procedure or something?
Yeah, so we do have a geometric check that I didn't cover here, but that's basically to make sure that when the relaxation is loose, we do not produce, or we do not like transfer our input straight to the drone just to make sure we do not crash. There's still a lot of future work left to actually analyze how the relaxations vary, or like the tightness varies. But yeah, we do have a geometric check to make sure that we do not pass an unsafe control when the relaxation is loose.
I'm not sure who is next here. Maybe we'll go here.
Hi. My question is for the voltage constraint activation. Am I correct in understanding that this compensates for the back EMF of the actuator per actuator? And the second question is, then do you think we can compensate for voltage drops on the power supply on the battery? Like for the voltage constraint actuation?
Oh, VRA?
Yes.
Oh, thank you. So pardon your question, please?
Yeah, so am I correct in understanding that it compensates for the back EMF due to the velocity of the actuator, that you have different torque limits, and with that, it's per actuator, but then can you compensate for, let's say, the power supply voltage because of multiple actuators?
Yeah. But from my perspective, it's not about compensate. It's the voltage is a motion representation for the motors. So our upstream controller can reason the behaviors inside the constraints from the hardwares. So it can truly achieve the kinematic feasible and voltage realizable behaviors and commands. Thank you.
All right, let's thank the speakers one more time, and you can follow up with them at the poster session.
All right, we've got two quick logistics announcements before the next session. So logistics announcement number one, if you haven't done so already, please make sure to get your t-shirts. We seem to have lots still up there, so you'll need your registration email at the registration desk, so please don't forget. And then announcement number two, just a very early warning about the banquet tomorrow. So tomorrow's banquet is not here. It's not at the conference center. It's a different location in the Rocks neighborhood. It's about, 20-minute walk from here. You will need your ticket to get in. So tomorrow when you come in, don't forget your banquet ticket. The back of the ticket has a QR code with directions on how to get there, and you'll also get those directions via email between now and tomorrow afternoon. That's it for logistics. So now happy to hand it over to Hannah for the next session.
40 minutes walk, so it's probably suggested to take light rails or trains from Town Hall to Circular Quay, then walk about 10 minutes. So make your own way to the restaurant tomorrow. Thanks.
I guess I walk fast. Okay, so good morning, everyone. We are now at the third Early Career Spotlight session. It's my pleasure to introduce Pulkit Agrawal. Pulkit is a rising star, having done many great works, both on the scientific foundations of robotics and their translation in industry. He is an associate professor at MIT, and he co-founded two companies, Eka Robotics and SafelyU Incorporated. He earned his PhD from UC Berkeley and bachelor's from IIT Kanpur. He has received numerous awards, including multiple Best Paper Awards, the IEEE Early Career Award in Robotics and Automation, and AROS Toshio Fukuda Young Professional Award. Without further ado, let's hear from Pulkit.
Thank you for the kind introduction, and thank you for having me. So today I'll talk about a little bit of history of how I got into robotics, and a little bit about my current perspective on what are the exciting problems. So when I was starting my PhD, there was this hypothesis in the field that if you do compression, you learn good features, and that's a pathway to intelligence. And that was inspired by what the brain did. It compressed sensory observations. It led to many exciting methods like ICA, autoencoders, sparse coding, so on and so forth. And the hope was that if you took an image and then you compressed it to a few features, you would learn the important underlying factors, like shape, color, lighting, so on and so forth. But if you go and run compression on images, sometimes you end up getting JPEG compression. JPEG is a really good compressor, but not a very useful feature. The point being that this compression was a very underspecified objective function to learn good features. Then I was wondering, okay, if it is not about compression, then how do we get to intelligence? Then, I tried looking at, what are, agents in the world doing, and what do they have access to? So most agents have access to their actions and what happens next. For example, if you have cars going around, they observe images, they know the actions that they take, and what happens next. So I thought, how about we try to correlate the observations that the agent is having, say xt and xt plus 1, with the action that caused that observation. So you could take xt, encode it into a feature representation z, same for the next image, and try to predict the action. Right? This is, for many of you, will be an inverse model. Right? So if you learn this inverse model using data, you end up learning these representations z. For this idea of playing around with observations and splitting them in two ways and predicting one part from another, was the early days of self-supervised learning. And then, over the years, with a lot of great effort put by many different people, it finally worked in 2020, 2022. And many of you today, use, SimClear, Moco, MAE, and, these kind of features. So naturally, the question is, the features which are good for vision, are they actually good for robotic manipulation? And I'm again going to go with my gut feeling or my gut reaction. Right? So if you want to do image classification, what you care about are things like invariance to position and pose. Right? That is how you classify objects. But if you're doing manipulation, you want to be equivariant to these things. So what my takeaway from this observation was that maybe this search for a universal task-agnostic representation is not going to succeed. And maybe instead, what we should pursue is an agent which can learn everything about the world so that when needed, it can use the knowledge which is required to perform the task. This naturally led me to say, hey, why don't we learn a model of the world, right? Which is if you have a current observation and the action, predict the next observation. And this is what people would call as a forward model or a world action model. Right? Models are not new to robotics, right? They have been there forever. And the idea of learning models was also not new. It was just exciting in 2015-16 to combine this idea of prediction with deep learning techniques back in the day. Right? Then the next question which comes up when you try to learn this forward model is what is the feature space in which we should make predictions? Of course, predicting pixels may not be the best thing to do. Right? So you have these images, xt and xt plus 1, encoded into some latence z. And we're trying to figure out what the z is. So at the time, I thought, I could use the inverse model to learn these features. Right? So you learn the features by predicting the action, and then you can run the forward model in that latent space. And then I was running these models back in the day. Today, if you do this, you wouldn't use inverse models. You would plug in Moco, SimClear, MAE, some other features. Right? So these were our experiments back in the day, robots going and collecting data 24/7 to learn these forward models and inverse models. And then we could see a current image, give a goal, and then ask the model to output actions. And then they would output actions so that you would move, say, an object from the location shown in the current state to a goal state. So as I was doing this work, I was thinking about, you have these forward models that we are learning. They take in observation and action to output what happens next. But really, these forward models are used to just infer actions, and that's what I actually care about. And these forward models are just a tool to infer actions. They're nothing more. But these models are hard to learn. They're huge, so they introduce latency, and they also have a high inference cost. So do we really need to learn these models in the first place? And as Vladimir Vapnik, one of the co-inventors of SVM, said, when solving a problem of interest, do not solve a more general problem as an intermediate step. So maybe learning a forward model is too general of a problem to learn policies, right? So using the same data that you use to train a world action model, you could just reverse the problem and just learn an inverse model, xt and xg mapping to a sequence of actions. Right? This is easier to learn, has lower latency, and has low inference, which is good if you want to deploy policies on a robotic system. Now, this is what one would call as a goal condition policies. And my hypothesis at the time became, well, if the agent needs to predict the future, it should emerge automatically of learning a goal condition policy instead of me requiring to build this in. And this led to this third hypothesis, which is intelligence is just about learning a policy that satisfies the agent's goals. Very simple in retrospect, but that's the pathway I reached this conclusion. Then the question was, OK, let's go implement this. And there have been, this conclusion is just not mine. Many people have reached this conclusion independently. I was just sharing my journey of how I came here. Now, over the past decade, there have been a lot of exciting developments. This is what we were getting back in the day with these goal condition policies. You could have a current image, you could give it a goal image, the robot would go perform this rope manipulation. It would kind of work, right, maybe 30% of the time. And one of the big reasons was the amount of data we had was quite limited. But over the past decade, there has been a lot of efforts in collecting data, but also advances in machine learning models. So now we have a new form of goal condition policies, what you can think of as vision, language, action models. And I like to think about robotics along these two axes. One is what I call as throughput, which means that if I run a robot for 8 hours, how much work does it do? It combines speed and reliability together. And the other axis is generality, which is how well does a robot work across tasks, objects, and environments. So industrial robots had very high throughput, but they were very, very task-specific. A lot of the modern machine learning robots, especially ones doing manipulation, lie over here, which is they are more general, but don't have as much throughput. Right? And the question which I've been asking is, how can we go to these generally useful robots which have both high throughput, but are also more general? So first, let's try to understand, why is this the case, right? Why do we need to speed up our videos many times? Why are robots slow? Why are they not as reliable when trained with machine learning? So let's think about a task, say transfer liquid. Typically, you have a task objective. We train a neural network model, which outputs some representation, say joint targets. It goes into robot dynamics, which then makes contact, and then you get the next state. So generally, at least in a lot of learning of goal condition policies, we don't really think about this dynamics. This is the work which is being done by a PD controller or something else. And we think of the intelligence lying in predicting the actions, which are, say, joint angles of the robot. And the way we are learning this intelligence, for example, in VLAs, is using human-collected data. And this data I call passive, because this is not collected by the agent, but was collected by the human. And a lot of this data is trying to map vision from actions. So in a way, it is doing this geometric reasoning about the world to decide where the robot should go. It's not really considering the dynamics of the system. But this is, the blue box is where a lot of interesting physical interactions happen. And so to push this to an extreme, here's a comparison I like to draw, thanks to Tony in my lab who came up with this slide. That very small changes in maybe the amount of force you apply or where you make contact can lead to very big changes in the actual outcome. And this is what this Rube Goldberg slide illustrates, how small changes can lead to very big outcomes. And this is also showing that these physical interactions are actually very messy. And if you don't pay attention to them, bad things can happen. So as an example, let me show you, these two policies which are trained on the same robot using the same data. Right? Everything, about the policy learning part is the same. Yet, one of the policies achieves, 5% success, and the other policy achieves, 71% success. And if you wonder, why is this the case? Of course, I didn't tell you all, all the parameters. What we found was that, different controller gains led to very different policy performance. The only difference between these two policies was how did we set the KP-KD of your PD controller, which is showing you that the low-level control affects what the performance you get when training a policy, right? And if you want to learn more about this, we're presenting this paper at this RSS, and we can also look at the QR code. The point being that we cannot really ignore this dynamics if you want to go towards high throughput manipulation, which means we want to be reliable, which means that we want to be high speed. Right? So what this leads to is that if you think about where I started, that if we look at the current state of ML robots, we need to improve them along the two axes. One is to make them more general, one is to make them more performant. So if we add more data, what we are doing essentially is going towards the generality axis. But just adding data does not necessarily improve the reliability and the speed at which the system is working. And the reason why this is the case is the following. So a lot of the data which is being used to train these VLA systems are what I call as passive data. Now, what do I mean by this? Right? So if you're learning a robot policy, or if you are learning an LLM, what you're trying to do is to maximize some objective function, say J. In both cases, we are learning a stochastic policy. But when we think about LLMs, for them, sensing, execution, dynamics, all of these things are deterministic. But in robotics, as we just saw, the dynamics part, the sensing, the execution, the dynamics, all of these things are very noisy. So the same recipe which worked for LLMs, where we took human-collected data to train systems, may not work. And if we really want reliability in the physical world, what we should be looking for is learning under the distribution of noise. Because if we learn in this distribution, we'll end up with reliable systems. And when we are doing passive learning, which is using human-collected or an off-policy data which was collected, somehow we are crossing our fingers and hoping that this data matches the noisy distribution, which may or may not happen. Right? The one way we can get this data is doing on-policy learning, where the agent samples its own actions, and therefore it sees the actual noisy data distribution. Now, one way to do this is reinforcement learning. Of course, there can be other ways you can also do it, for example, with MPC, but at least RL is one way of doing it. Right. So the first thing I'm going to talk about is that if you want to go to more reliable systems, we should put more effort towards interactive intelligence, which is collecting data on policy instead of passive intelligence. And as an illustration of this, we were looking at this furniture bench data set, where the goal was to assemble these parts. And first, we collected a lot of demos. And what we found was the performance saturated. Again, not news to people in this audience. Then, we collected data with interventions, or using Dagger, where you could let the agent correct for its mistakes using an expert. The performance still saturated. And all of these experiments were in simulation, so we could really turn different knobs to ablate what was happening. And what we found is there were these very small errors. For example, a part might be misaligned, or you get an unseen pose of the object in the hand, and you wouldn't really get the data of how to do recovery. And then what we did was, went ahead to add, we took this BC policy, trained from demonstrations, but just added an RL residual, which was collecting data on policy and also ran at a higher frequency. And once we did this, the performance across a lot of different tasks improved substantially, really showing that how much gain in performance is coming from interactive data because you are sampling the right data distribution. Now, the big question we're doing on policy learning is, where do you get this data from? Because doing this in the real world can be very expensive. So what we have been doing in my lab is to collect this data through simulation, right? So we can go and sim, in short amount of time, collect large amounts of data, train policies with RL, and then, we would get these behaviors in simulation. Now, over the years, we and, other labs have shown that things in simulation can be transferred into reality. So here was some of our early experiments showing a mini cheetah breaking the speed record. Here is a robot, spinning around. One day we took a robot outside the lab, and the screw in the motor, became loose. But you still see this robot limping, but it continues to walk. Right? Or here's a robot, dribbling, soccer ball, and everything is running on board on the robot. Everything trained in simulation without any, real-world data collection. And here's another example of where we wanted to push how athletic the robots could become. So over here, the robot uses its entire body to figure out how to throw the ball as far away as possible. We later, also scaled these results into the problem of in-hand reorientation, where these are, hand trying to reorient objects in simulation, but then, transferred into reality, where we are showing new objects the hand hasn't seen before. These are, non-convex shapes. The hand has to fight gravity while it is reorienting them to the goal orientation shown on the top right. And it's using a depth camera and proprioception as input to go to the goal orientation. And we could take this reorientation controller and also apply it to new objects, for example, the squash, which is being rotated, so the second hand can come and peel it. So looking at these results in retrospective, what did we learn about sim to real? Right? The first thing that we learned about sim to real is that sim doesn't need to model the real world perfectly. It just needs to emulate the right force profiles to which the robot should react to. Now, what do I mean by that? So, we had this result where this robot is going over a hill made out of gravel. So one might think that if you want to get sim to real transfer to happen on this scenario, you have to emulate gravel, right? And emulating gravel is going to be very challenging, right? But if you think about the problem, what's happening is when the quadruped hits the gravel, the stone slips down, and then there is a force of gravity which is pulling the robot down. So if you know how to react to slip and a downward force, that is sufficient for you to learn a policy to go up a gravelly hill. So you could have a very simplistic simulator with a little bit of uneven terrain, randomize the friction, apply a lot of randomized forces, and you will induce the same force profile. So therefore, very approximate simulators, if they induce the right force profile, enable us to learn quite robust policies, right? So this goes back to the same argument that I was mentioning earlier, that policies are sometimes much simpler, as opposed to forward models that, if one considers a learning problem. The second thing, that we, found to be, important is, of course, domain randomization. But if you do too much domain randomization, then policies become conservative. So inferring, properties like friction and mass as a robot is deploying its policy ends up being useful, especially if you want to do very aggressive maneuvers. But if you're not doing aggressive maneuvers, it doesn't end up mattering so much. You can just do simple domain randomization and things work. Sometimes, for example, when you're dribbling a soccer ball, adding some simple augmentations to the simulator is useful. You don't have to go and emulate sand and grass and pebbles. You could add a simple drag model. And the intuition is, again, the same. You just need to emulate the force profiles. And if till the time you do it, sim to real will work. The other thing which is very important is learning the actuator models. What does actuator model means is if you have your current state and a desired state, what is the torque that you output? That has to match between sim and real. But in many scenarios, we don't really have torque sensors available to us. So I don't have time to go into details of it. But for example, if you have a policy in sim, and if your actuator model hasn't been trained, most likely this is what's going to happen. The robot will not work. But we came up with techniques where even if you don't have torque supervision, you can learn these actuator models to enable sim to real transfer to work. Right? And lastly, designing a curriculum, designing reward functions to prevent infeasible and undesirable behaviors was important. But if you do things which I said on the top, the amount of reward design you have to do ends up reducing. So still we have to do reward design, but at least we have some guidelines that can help us reduce the amount of work going into reward design. So until now, what I talked about was, the more interactive we become, we can increase the reliability of the system. So the next question becomes this, hey, can we go and scale this up, even more, right? And when it came down to, scaling things with humanoids, a very popular method is motion tracking, where you have reference trajectories shown in purple, and the humanoid is trained to copy these reference trajectories. And with this, one can get these beautiful videos like this robot dancing. But the one thing to notice is that there are no humans around this dancing video, and nor is this robot making contacts with its environment. Right? And if you had to give this motion reference, but there was something the robot has to contact with, it will completely be unaware of it. Because now it has optimized how to follow positions very precisely, just like a stiff factory arm, which is not good for contact-rich interactions. So what we did was to come up with a technique where we can still remain close to the reference, but the robot can regulate its own forces. And this is what we call soft mimic. And now, if, for example, the robot is trying to pour something out of a bottle, if someone applies, large amounts of force, it will cause, large motion. But if the robot is compliant and is force aware, then the robot behaves much more gracefully. And the same happens to if you take a walking policy, without any additional pre-training, if you put a heavy payload, the robot learns to adjust to this payload. Or if a human goes and interacts with it, the robot will also behave gracefully with respect to a human. Right? So making the robot more force aware helps it make contacts, but also be safer around humans. Now again, this idea of forces is not new in robotics, but it's been made explicit in learning-based control so that we can deal with contacts much more naturally. Now, all of these results on legged robots are good, but what about manipulation, right? I mean, we are getting this fast, rapid locomotion, but manipulation still remains slow. Why is this the case, right? So to gain more insight, let's think about a scenario where you have to go pick up an object kept on the table. So a typical way to build a system would be to say, let me use a vision system to predict where the table is and where the object is, and then I will move the gripper so that I do not hit the table. Because if I hit the table, I'm going to either break the table or break my gripper, especially if I'm moving fast. So what you end up with is a motion which is very careful, right? It's very careful in how it goes and picks up the object. And so one can think about this approach as trying to not use contacts. But if you look at how a human is performing the task, the human is not afraid of touching, right? So the human goes at full speed, touches the table. The touch is important for two reasons. One, if your vision is imprecise, then the moment you touch, you know to close your hands, which means that you can deal with imprecise sensing. Second, you can go fast. And I think these two things can happen if we leverage contacts, right? So the idea behind what I'm going to now call force intelligence is to make contacts our friends and not our enemies. Right? And what do I mean by force intelligence? Right? By force intelligence, I don't mean the choice of action space to be position, impedance, or forces. I also don't mean just putting force or tactile sensors. What I really mean over here is optimizing the full stack of hardware, sensing, and control so that it makes contact-rich interactions easier to learn. Right? And historically, the reason we didn't have it, at least for general purpose manipulation, was that we were building off on these industrial robots, which were really optimized for doing precise trajectory tracking over and over again. What this meant was that you would have robot arms, which would be very stiff, and you would do high gain control, so you could control positions very accurately. But once you design your system for positions, you don't end up designing it for forces. Right? And to illustrate this, let's think about this example. So typically in manipulation, your hand is quite heavy, and the objects that are being manipulated are quite light. And this becomes the source of many of the problems. So to understand this, or to get intuition behind this, let me ask you this question. Suppose there's a chair, and there's a pickup truck. Now you have to sit in the pickup truck and drive it to move the chair. So how would you drive the pickup truck? Slowly? Okay, great. The reason you end up driving the pickup truck slowly is because you're afraid of of hitting the chair and making it fly away. And this is why a lot of manipulation remains slow, because the physics comes in the way and there's a big inertia mismatch. Right? The second thing we can do is to say, let me put tactile sensors and do high control frequency on top of it. Right? But the challenge with this is that my control frequency has to become really high to detect contact and react to it. Now, if I have high control frequency, this is not very good news for machine learning, because as the control frequency increases, the horizon of the problem, both for imitation and error, increases, which is bad. So instead, if we could match the inertia between the hand and the object, and we could have properties like backdrivability and high bandwidth, we can make the problem easier for machine learning by essentially reducing the control frequency at which machine learning has to operate. Right? And this goes back to this idea of moving beyond geometric intelligence into force intelligence. Right? So apart from just matching inertia and being backdrivable and high bandwidth, there are other questions which come in. Right? For example, what is the role of skin-like tactile sensors? And through experiments, which we haven't published yet, but it's an ongoing study, what we have found is the higher fidelity of tactile sensing you have, the higher throughput you end up getting in manipulation. And this high throughput framework also helps us answer debates like how many fingers one should have. Right? If you have 2 fingers, then if you have to move an object, you might have to pass it to a second hand, again re-grasp it. Versus if you have more fingers, then you can move the object more faster. So in some ways, having more degrees of freedom ends up helping you go faster. So if you only measure accuracy, the effect of tactile sensors, the question about how many fingers you should have, is not known or will not come out. But if you start measuring throughput, both the role of number of fingers, but also tactile sensors becomes more important. And I know I'm almost on time, so I'll just wrap up in a couple of minutes. And this is what inspired us to make this hand, the eyesight hand. And we made this hand to be low inertia, using quasi-direct drive, be highly backdrivable, but we use this insight that most objects of everyday manipulation weigh less than 2 kilograms, which means that we can use current motors to still achieve these properties. So this hand moves fast. This hand is covered in tactile sensors, which are high resolution. These are gel site sensors from Ted's lab. but we also made this hand in a way that loves making contact. And yet it can manipulate things which are roughly 2 kilograms. And this hand is super compliant, so you can use, for example, a card and move it. So it's really designed for doing force tasks. Then to see what this hand is actually capable of, right, we connected this hand with the human hand with these mechanical linkages to really see what are the kind of tasks that can be done with the hand design that we have. And what we found was that if you have mechanical linkages which communicate the force at a joint level from the robot hand to a human hand, the throughput at which the human is doing these tasks increases. And this is what we quantified in this paper, DEXOC. So in summary, if we want to increase our throughput, which means increasing our reliability and speed, I think there are two things that we need. One is interactive learning, and other is hardware which is built for contact-rich interactions. Right? And by combining this, we can start moving towards these generally useful robots. Now, once we try scaling these systems, there are questions which come up in how do we do reward design, how do we do environment design, which remain open questions, which are very exciting to study. With that, I'll stop over here, and thank you so much for your time.
Thank you. Thanks, Pulkit. Great talk. So we are actually running out of time, and we have our coffee break outside. But if there's a very quick question, perhaps one, we can take it. Otherwise, we can go for the break and ask all the questions you want directly to Pulkit. So perhaps while we are, perhaps just one very quick question, Pulkit. So I like that you're mentioning about this interaction between the force and the geometry. So I'm actually curious, in this interaction, do you see what kind of problems do we need more geometry? What kind of problems would we need more forces, for instance?
Yeah, so I think the goal is not to say that geometry is not required. I think geometry is good to get an initial plan. And then I think the last millimeter problem is all about forces. Yeah. So we should solve the last millimeter problem through force interaction, but use the geometry to get the plan which helps us go towards the object.
Okay. Yeah. Okay, so perhaps very quick from Luca.
Pulkit, great talk. I had a question. You spoke about sim to real. You made a point about what you care about is simulating the force profiles. You had a lot of comments about sim to real from the physical standpoint. When we start using cameras and appearance matters, what's your take there? What matters, in terms of reducing sim to real with images?
Yeah, so I think a lot of the sim to real work, has happened with depth cameras, which have gone beyond using fiducials. I think getting sim to real to work from RGB, I think we have starting to see good results in navigation. And I'm confident, at least with what we are seeing, the same can be scaled up even for RGB style manipulation. So I'm confident that we would, just like today when we do imitation learning, we use very general camera systems. Similarly for sim to real, we will also be able to use very general perception backbones for it.
Okay, so I think we are really running out of time. So thank you so much for Pulkit again, and thank you so much for everyone in staying. We have coffee break outside. Hi, my name is Hannah, actually. Nice to meet you. Yeah. So I'm actually curious when you say you actually, maybe you want to pick up as well. So when you say you don't actually need such a high accuracy in the certain. So I've been working on mentioning is that it's because you can actually utilize just the forces.
Yeah.
So then when we start having larger problems like present problems, then it's not just the last mile. So that this additional everything how we
So not until now, I think I've been focused mostly on the short horizon problems to make it well. Because I think the long horizon problem, the main challenge is that how good is the short horizon control. If you can make it good, then the long horizon also becomes
to some extent.
yeah. So I think what we're trying to do is to do more bottom up to make the short horizon very good.
Thanks a lot.
Yeah, thank you.
You've checked your presentation?
I'm good. Yeah.
You good?
We do have sound.
So it's picked up straight away. 1024 768 will fill that screen, so we needed that raise.
So the first. Oh, good. It's not working. There we go. It's Google Slides. You're sarcastic, right? Okay. Yes.
Lift that for a second. This is like a college lecture.
I see.
Something in the audio backgrounds.
Yeah, so we'll need sound for this one.
Yeah, that's what we're doing.
The rest is fine. The rest is just me.
So when you present, I'll show you that. I won't put it on the screen until I see it in full presentation mode. I'll just go check your audio for you.
And resolution, everything is fine?
I'll quickly flick that up so we'll see.
Thank you. And you're going to get this typical plot 5 minutes.
Sounds good. I've noticed you guys are nicer to the sponsors than yeah. It's Kina? Yeah. Moscow. No, I don't know. I've never met anyone else with it. Yeah. No idea. I think it's a town somewhere.
Cuckoo's call, pendulum swings. Thought you knew everything.
Give it 2 more minutes if that's okay.
Make the cross.
I can't tell if they... Did they get the sound? And I want to check a couple more videos. I'm sure they're all okay. Again.
But I feel somehow strangely compelled. Under moonlight I stood wild and naked. I felt no shame, just my spirit awakened.
Again, I'm closing
Sinner. Seeing everything, got my eyes, got my face.
I don't know.
Fireball drop from the sky. All my dreams have come to pass.
Yeah.
Where's my faith?
calling a guy, so I think this is not
See it till I cast it off. Sinner, there is no such thing. Beginner, I have learned to sing. Forever, I must walk this earth like some forgotten soldier. Today I am still disconnected to the face that I saw in the clouds.
No, that.
Yeah. And the closest I get to contentment is when all of the barriers come down.
It's not better in the desk, so I just did the audio.
These things I should keep to myself.
Okay, I can play the rest of the videos from now to make sure.
But I feel somehow strangely compelled. The closest I get to contentment is when all of the barriers come down. Sinner.
All these people.
Hey buddy, I'm just checking a piece of audio from stage. I can't see it on the console. You can? Scroll back, please.
I go back to the audio one.
Yeah, maybe if we can go into audio to make sure it's sent to audio as well.
Go ahead.
Sure. Where's your audio?
Sun is going down, time is running out, no one else around. Steady losing life, steady losing my mind, moving shadows around.
Because I'm not in a Zoom.
Without you, there ain't no place to
Sometimes this decimator, which is the vision interface, takes the audio. So it has a bit, which is good. It's for like home stereos, so you here's a cool track.
Let me keep going for my videos.
Just check the somebody just before you present, if somebody's just before you, can put your laptop underneath and bring it up.
Alex having some cloud in my head. What you waiting for? Something physical. I can do this by
It's a hell.
without you. There ain't no place for me to hide. Without you, there's no way I can see tonight. I do
As long as you're
a
up
little bit of peace and quiet. Without you, I keep slipping in a bad
Do you want me to try the audio again? Sure. Yeah.
Resolution to be 1024/768 to 50.
Thanks.
Doesn't it automatically adjust that based on the HDMI? So
Yeah.
HDMI doesn't scale.
Baby, you wish I sugarcoated that day. Sit back, Coca-Cola, hit the highway. We fly
Now what?
past them in the fast lane.
In the email, they said 12:30 to me. Isabella? Should we keep one then? It was saying one on the, yeah, I have 12:30. Got it. Okay, that's good. Can we do 12:50? Thank you. Well, also, and update that. Yeah. Thanks. Still waiting?
Still waiting.
Do you want to try the other video?
I think that would be good use of time if I was going to try it, but do you want to show whatever?
Pick me up. Yeah, you pick me up.
I think the sound is to the other side.
Ain't no love that's quite like our love. I get high just from your sweet touch. 'Cause there ain't nothing sweet like, no, there's nothing quite like. There ain't no love sweet like, sweet no love.
Would you hear the sound now? Or?
Literally 1 month travel, I think.
We would. Your video isn't actually quite clear now. Taking a whole frame here.
Yes, but that's.
You fine with that? Okay.
Yeah, that's the video they sent me.
But you can resize it and push it out a little bit. So
Yeah,
that
it's
it
fine.
looks like- Okay, cool.
Okay, I can do that.
Well, yeah, I don't know if they're going to do this. It's supposed to be starting at 11.
But how can we check if the sound is working?
Okay, so just wait till my colleague gets back.
Thank you.
Oh.
Sure. All right, let's move on then.
But I do need to know before that.
Yeah, so do we.
There.
Yeah.
So what's the plan?
The plan is to wait. This is a scheduled break.
Time is
So that's a waste not here.
Yeah, but I mean, we can only test during the break, right?
That's that's the.
Wow. Okay, so what should I do? Should I come back next time or?
When do you present?
At 3?
At 3. In the break. Yeah.
Okay.
Because I'm right after.
Are you? I'm first on.
No, I'm 11:40, but
Looks like
there's
there
a
has been
session.
a little bit more focus on the user stuff, like the use cases. But
Do you have a set of headphones?
I feel like there's a lot of
I mean, I know that the sound works if I just turn the sound on, but
what is it?
Just the issue is
So what is it needed? Because this is what Project One is about. So that's what I figured out.
yeah, I was totally next to
now.
when you were saying, because you know, it's kind of like they start build you up? Advice. Did it break you down? We're thinking about what's the next steps to implement, and then we got this like, just like very like
Mass estimation and this and that. I was like,
Thank you. I think we're good.
You don't leave your laptop here?
No.
Okay, cool. So as soon as I see full screen, I'll put it up for you. Great.
Yeah,
And I'm really like, I was kind of like thinking about our workshop.
Did it work for her?
Like, I feel like, you know,
That is a good thing.
start in the field and then come back to the
I don't necessarily need that now.
problem we actually need to solve. And they're just like not doing that.
I think
They have all these like great teams.
Hello,
doing
RSS.
great work.
Hello, Oliver. Greetings from Austria. It's great to see that after all these years, the contribution of Johan is still relevant today
I
in
still
this field.
remember that
Great.
they made all the
Thank you.
You're welcome.
at the end, Tom said, this one is not going to work. still have different kinds of arms, different kinds of all that things. And so it's yeah, it's going in a very different way. Yeah, this is
Yeah, well, I guess, you know, like the four big ones. It's like a lot more effective.
Yes.
Just don't look into the light. Listening to the presentation, having time for, you know, one quick question each.
Yeah, it was.
Okay.
And then they confirmed the date so last
So
minute
long.
that I already had something. And so I was like, I have to run.
哇，好安心啊！这个电脑在这里。They were just going to send us the reports and
It was asynchronous.
yeah. So then when they were like sending us like it's happening on the 7th, I was like.
I hope, I mean, next year is the final year, right?
Yeah, I think so. I hope we don't organize something in person.
I hope they do something to show.
Yeah, it's really.
Is this how, generally, I mean, this is only my first experience in actually really intimately getting involved with European projects. Is this how generally it happens? Like you propose something, but what you actually do is like.
Well, this is kind of an unusual European project because it's being funded. Like most European projects are funded.
Right.
And this project is very strict. It's too strict. It's like whatever you promise you.
Oh.
But this is, like, you know, it's being funded by the local city, Karlsruhe.
Yeah, the Partenkirchen.
And then there's always these like
Always they distribute.
so it's very unusual. So I don't know. Like I'm very curious to, you know, I see. I would really like to see reports.
Yes.
You know, but I don't get to see the cameras or.
I will be.
I would like to see what the industry is. I feel like they must be overwhelmed. You know, like, I'm just like so sad because like they have this amazing infrastructure. They have this big they have the nursing.
It's so amazing. When I first was so excited. I was like, okay, finally, this is like a whole another university that is focusing on this. Like there's a care home right here. There's like faculty. It's like so exciting. And also there's been, you know, there's been change in personnel and everything, right? So it's.
But like I think what I think is to like figure out because they're having these issues.
Oh, okay. We have 3 minutes, I guess. Yeah, I agree. Because I think I'm getting started. So.
This is your lady.
It's true. It is just start at 11?
I assume so. He will tell us as the guide.
Actually, let me ask quickly. You'll just do like this and then I can see, okay, it's almost go time. Hey, good to see you.
Hello, welcome everybody. Hope after the coffee session you're a little bit more fresh. Dana Kulik and me, as session chairs, are welcoming you for the HRI session. And we'll get started with our first paper on automated synthesis of facial mechanisms for conversational animatronic robots. The presenter would be Zhongzhen Zhang.
Hi everyone, I'm Zhongzhen from Tsinghua University, and in this paper, we asked whether a single portrait can become a physical conversational animatronic face. Our system automates two things that are usually handcrafted, the internal facial mechanism and the speaking and listening motion that drives the emoted-turn dialogue. Existing half-adapted animatronic faces are impressive, but they are essentially bespoke machines. Every new identity needs a new actuation layout, new linkages, and many rounds of CAD debugging. This is the scalability bottleneck. We want a pipeline where new face geometries are not manual engineering projects, but computational design inputs. The starting point is the reusable parametric template. We decompose the face into semantically meaningful models: eyebrows, eyes, mouth, jaw, and neck. And the topology and actuator layouts are shared across identities, but their placement and linkages parameters can be optimized. This gives the optimizer structure while keeping enough flexibility to fit different faces. Given a portrait was reconstructed 3D head mesh and semantic landmarks, then the design runs hierarchically. In the inner loop, each expressive model is optimized locally. Action unit-derived trajectory define what the attachment point should do. The atomic guided volumes define where it takes a lot to move in the outer loop. We assemble the full CAD, check collisions, and use MTB updates until the design becomes collision-free. So the loop jointly targets expression and manufacturability. This is the visual evidence for scalability. The same template is synthesized for 8 very different morphologies: realistic humans, stylized characters, and non-human faces. Yuda and the elf are intentionally hard cases because their volumes and proportions are far from the main templates. But the system still creates valid internal assemblies instead of requiring a fresh manual mechanism for each identity. Quantitatively, the hierarchy is important. Our method reaches the highest success rate on 15 heads while keeping similar expression amplitude. Compared with expert manual design, mechanism design time drops from roughly 22.8 hours to about 11.7 minutes. Hardware alone is not enough. A conversational face should not only lip sync while speaking, it should react while listening. We therefore feed two-speaker audio into a tone-wire model that predicts bland-shape expression and high motion. Then semantic region-wise registers plus Nike inverse kinematics translate this digital motion into physical motor commands in real time. Here are 4 demonstrations of the complete chain. First, live human-robot interaction shows real-time spoken dialogue.
Mentor, what do you want to teach me? How to be a human.
Second, the hybrid avatar-robot interaction shows transfer between digital and physical embodiments.
Back immediately. But I can also smell the flower, see the blue sky.
Third, Titanic shows speaker motion and listener back channels between 2 physical robots.
Rode a horse, jack with my legs open.
Like a man.
Finally, Star Wars stresses different face geometries and speaking styles.
Does it matter? Look at you, young Luke. Old you have become.
Master Yoda, did I live up to your expectation?
The full video can be seen on the website. To summarize from one portrait, we've synthesized the collision-free mechanism, fabricate a personalized face, and drive it with speaking and listening motion. This makes animatronic faces scalable and moves us toward many personalized robotic identities. Thank you.
All right. The second paper is on social human-robot embodied conversation dataset, benchmarking foundation models social reasoning, presented by Suyeon Jung.
As social robots become more common in real-world settings, their success depends on understanding complex and nuanced social interactions. While recent foundation models have shown significant progress, it is still unclear how well they reason about the unique social dynamics of human-robot interactions. To address this challenge, we present a social human-robot embodied conversational data set that includes 400 human-robot interaction data from 3 real-world longitudinal studies. While building this data set, we applied GAN and diffusion-based anonymizations to protect participants' privacy while preserving important behavioral cues such as facial expressions and gestures. Our data set was annotated based on 2 key concepts. First, we defined social competency as behaviors that help the interaction, such as showing empathy, listening attentively, or taking turns naturally. On the other hand, social error is defined as behaviors where the robot deviates from the user's desired or expected response that degrades the user's perception of the robot's social competence. Based on these 2 core concepts, annotators watched 2 short segments of the data and labeled whether the robot's behavior was socially competent, socially erroneous, or neither. They also annotated the source channel of the behavior, whether the evidence comes from the robot's verbal behavior, nonverbal behavior, or both. We then asked the annotators to identify which social attributes were involved in such competency or error. These attributes are grounded in prior HRI taxonomies, such as emotions, engagement, conversation mechanics, knowledge state, intention, and social relationships, and social norms. Annotators were also asked to provide rationale on why they consider the robot's behavior competent or erroneous. And for the social errors, they provided a corrected actions, what the robot should have done instead. And this is important because many robot failures are subtle rather than obvious. For example, a robot may have technically answered to a user's questions correctly, but interrupted at the wrong time, failed to recognize emotions, or ignore conversational cues. Now that we have created these labels, we investigated whether language and multimodal foundation models could reason about robots' communicative actions. We evaluated these capacities through a set of benchmark tasks. For example, can the model detect when a social error occurs? Can it identify the type of error? Can it understand the flow of interactions? Can it explain why a behavior was wrong? And can it suggest how to fix it? We conducted an evaluation on how foundation models such as DeepSeek R1 can reason about real-world social interactions, and how their performance are compared to that of human annotators. We evaluated several state-of-the-art foundation models for this benchmark task and found that current models still perform substantially worse than human annotators across nearly all of these social reasoning tasks. But we also found some interesting patterns. As models are updated or scaled, their social reasoning capacities tend to improve across the board. And models from similar families actually tended to show similar shapes on the radar plot, which suggests that these consistent reasoning patterns may come from similar data sources, architectures, or training procedures. Our study suggests that foundation models still have significant limitations in understanding social interaction involving robots. So we invite the RSS community to check out their paper, data set, and code to work towards socially intelligent robots and multimodal and AI systems. Thank you.
Great. The third paper in this session is K9, Coaching Visually Impaired Users for Interactive Navigation with a Robot Guide Dog, be presented by Chunjun Yu.
Hi, everyone. I'm Chunjun. I'm here to present our paper, K9, Coaching Visually Impaired Users for Interactive Navigation with a Robot Guide Dog. For 2.2 billion people worldwide living with visual impairment, robot guiding systems are maturing and promise a future of autonomy. It can help users navigate unfamiliar environments, avoid step obstacles, find destinations, and complete everyday mobility tasks with greater confidence and independence. However, effective use will require subtle human-robot coordination. The user can become the bottleneck, as such tasks often require precise timing, positioning, and coordination with the robot. Let's consider a task of navigating to a restroom. Two common failures may arise. When the user is trying to open the door, the user searches the wrong area for the handle. During entry, the user may follow too closely to the robot, obstructing its path and creating a collision risk. That motivates our central question. Beyond building a robot assistant, how can we actually build a robot coach that can help with human skill learning? We present K9. K9 is an automated coaching system that helps visually impaired users to learn interactive navigation with a robot guide dog. It takes first-person view images as input and generates language feedback to improve user performance. Since interactive navigation is a complex task involving multiple coordination stages, K9 first decomposes it into manageable sub-skills that can be practiced individually. It then operates as two different levels. First, we call it inter-skill level, where K9 selects the next sub-skill to teach the user. And the second, intra-skill level, where K9 diagnoses user mistakes and provides corrective feedback after each training episode. At the inter-skill level, K9 decomposes complex tasks into like navigate to door, open door, and enter room. It tracks users' proficiency on each different sub-skill over time and selects the most appropriate one for training. For example, if the user struggles with locating or opening the door, K9 focuses practice on that specific sub-skill. At the intra-skill level, K9 provides actionable feedback to the user. By using a vision language model, it first describes users' behavior over time, summarize them into an interpretable timeline, and then generates actionable feedbacks. It can also adapt robot behavior to create diverse task scenarios, providing additional learning opportunities for the user. We conducted a human subject study with blindfolded users and a case study with a visually impaired user. On the left, you can see the uncoached behavior of the user. It drifts away from the door frame and crosses the robot. On the right, after coaching, the user reaches handle immediately and steps back to create clearance, resolving the coordination failure. These learned skills generalize to different routes, orientations, and users. Finally, we extend K9 beyond navigation. We also apply to a robotic handover task, enabling the user to grasp a variety of objects from the robotic arm. To conclude, I would like to quote, we shape our tools and thereafter our tools shape us. We do envision a future where robots are not only assistants, but also capable teachers, helping humans learn new skills and master a wide range of everyday tasks with different tools, objects, and environments. And I will see you at the poster session. Thank you.
Awesome. The next paper is QuickLab, Quick Language Action Preference Learning for Autonomous Driving Agents. It will be presented by Nathan Denler and David Lee.
Hello, I'm Nathan, and this is David. We're very excited to present our work on performing online updates to robot policies from multimodal feedback. Imagine a robot moving up. It can go close to the table, and it has these different feature weights, and the weights you can trade off on the trajectory features to change the robot's trajectory across a variety of reward functions. However, as the robot executes the trajectory, a user may notice that the robot is optimizing for the wrong set of feature weights and provide a correction, like this, and a language explanation for why the robot was wrong. The fundamental problem is that learning from these two reward function feedbacks is ambiguous. So imagine you're the robot and you can only learn from the physical correction. Technically, the user increased distance to the laptop, decreased distance to the bottle, and went higher above the table. Now, if you look at just what the user said, in the absence of the physical state information, you don't know what the robot was going too close to. Was it too close to the laptop, to the bottle, or to the table? But if you combine these two types of feedback, the robot can figure out that the user actually wanted to stay away from the laptop. Our core research question is, how do we combine these two sources of feedback to resolve ambiguity? Our approach uses language as a probabilistic observation to modulate how the robot interprets the physical corrections. We extend previous work that models the posterior over the weight update as a prior times the probability of a physical update, and then we add on a language component. Our algorithm has 3 parts. First, we assume that the robot has a prior over feature weights that the person cares about, and the user has provided a physical correction and a verbal explanation. For the physical correction, the weight update is the difference between what the robot originally planned to do and what the human moved it to do instead, which has a nice closed-form map approximation. To model the user's language, we use an LLM to estimate the probability of the user's explanation by passing in the language utterance and a textual description of the environment to predict a mean and variance score. We combine these feedback probabilities into a closed-form update rule. The high-level idea is that we can take the prior weights, add a physical component gated by the language confidence and the prior confidence, and add the language component for each feature weight.
We evaluate our algorithm through 2 user studies. One was in a simulated tabletop manipulation environment with robotics experts as participants, and the second was in an autonomous driving scenario with participants from the broader MIT community. In each study, we compared 3 different methods. The first method used only physical corrections. The second method gave the physical context to an LLM for it to predict the update, but did not use our full closed form rule. And the third method is our full method. In the tabletop manipulation setting, we measured the error between the learned behavior and the ground truth behavior. Physical had the highest error, while LLM only and QuickLab had lower error. In the driving scenario, physical only, again, had the highest error, while LLM only and QuickLab had successively lower errors. We hypothesized that QuickLab did better in this scenario because non-expert users use much more imprecise language, indicating that our method is more robust to language ambiguity. We also had users rank QuickLab using subjective constructs and found that users preferred QuickLab overall. Thank you for listening, and if you have questions, I'll see you at the poster session.
Thanks.
Okay, the next paper is Robots That Know What to Ask, Recovering Misaligned Rewards Through Targeted Explanations. It will be presented by Helena Merker.
Hi, I'm Helena. I will be talking about how robots can recover misaligned rewards through targeted explanations. Consider teaching a robot to carry a cup of coffee across a cluttered table. You care about several aspects of the task at once, but demonstrating all of them simultaneously is difficult. Concretely, let's say you vary the cup orientation and the distance to the laptop, and the robot learns an incorrect reward function. At deployment, the robot spills the coffee on the laptop. And this is the core problem. From the demonstrations alone, the robot cannot tell whether these features are unimportant or simply whether the demonstrator never showed how to handle them. Therefore, the question we are interested in is, how can robots detect which features are underspecified in uneven demonstrations and elicit the right feedback to correct them? We introduce our framework, which we call ASK. It has 3 stages. detecting which features are underspecified, eliciting targeted demonstrations from the human, and then using weighted reward learning to combine the new demonstrations with the original ones. So how do we detect this reward uncertainty? We could look at the feature values across all the demonstrations and how much they vary. Our key insight is that a feature the demonstrator reliably optimizes shows low variance across demonstrations, while an underspecified feature has a wider range of values. For each feature, we build reference distributions of its variance under optimized versus non-optimized conditions. Detection is in Bayesian model selection over subsets. So which hypothesis about which features were underspecified best explains the observed variances. At deployment, we select the subset of features with the highest posterior probability, here cup orientation, distance to laptop. And this lets us build a targeted query. The robot generates a natural language explanation naming the features it's uncertain about, and requests demonstrations that explicitly address them. Reward learning usually assumes that every demonstration comes from a single Boltzmann noisily rational human with a rationality coefficient beta. But our two sets reflect different attention regimes, so we use separate beta vectors. For the initial demonstrations, beta is high on the well-optimized features or low on the underspecified ones. For the targeted demonstrations, it's the reverse, and we call this weighted reward learning, where demonstrations are weighted with uneven rationality vectors. We evaluate first in simulation. Let's say we have a simulated Boltzmann rational agent that underspecifies the coffee feature. We first see that querying about random features gives some reward improvement. Ask elicits demonstrations on just the detected underspecified feature, which already works much better. And then weighting the demos to emphasize the underspecified feature retrieves even more. We also see similar results when other features are initially underspecified. Simulation, however, cannot tell us whether real demonstrators respond this way, so we conducted a user study with 12 participants on a physical Frankel arm. If you were really trying to give feedback to a robot today, probably the robot wouldn't give you any guidance. Maybe you could simply watch its behavior, and with our method, the robot will ask for feedback on a specific feature. So does ask actually help? We did find that demonstrations elicited through feature-based explanations yielded significantly greater reward recovery. One thing worth investigating, however, is how much of this improvement is due to the demonstration-specific weighting. We do see that weighting improves every condition, but it presumes that the demonstrator attended only to the named features, an assumption justified only under explanation where we directed their attention. The participants themselves corroborate this. Under explanation, most people emphasized only the underspecified feature, hence the orange-only region is the largest. However, subjective preference was split. Some participants preferred being told exactly what to correct, while others preferred simply adjusting a behavior they could observe. And this suggests a design opportunity, perhaps combining both the rollout and the explanation might capture the best of both worlds. Thank you for listening.
Our next paper is Embodiment Meets Environment Towards Context-Aware Safe Physical Caregiving Robot, and this will be presented by Zhangjun Wu.
Hi everyone, I'm Zhenxing from the Empress Lab at Cornell. I'm finally presenting my own work, Embodiment Meets Environment Toward Context-Aware Safe Physical Caregiving Robots. Physical caregiving robots need to assist the user wherever they are, in public environments, at the office, or at home, across various tasks. Each of these scenarios comes with its own physical and social environmental context. They may also come in different embodiments. For example, prior work has used robots such as Kinova and Franka. These robots may also change their embodiments by using different tools for different tasks. For example, utensils for feeding and sponge for bathing. Existing works are always tied to a specific environment or a robot. Because of that, moving the system to a new environment or a robot often requires manual configuration. For example, a feeding system that works in a home setting may not directly transfer to another robot or adapt to a hospital setting. This motivates our focus on context adaptation. Therefore, we propose E2Care, context-aware physical caregiving robots. In our framework, we treat primitive skills as interaction templates that are reshaped online based on the context. We represent the environment and the robot together in a unified 3D dynamic scene graph. For the environment, we use observations to build a dynamic scene graph with multiple layers, including objects, rooms, and floors. Each node contains semantic information, like a text description, as well as 3D geometric information. We also represent the robot itself as a kinematic graph in our 3D scene graph. Once we have the complete scene graph, we will first extract a task-relevant subgraph. Then we generate constraints using a large language model. We have two types of constraint here. Hard constraints are predefined and should never be violated, such as self-occlusion. And soft constraints are generated by LLM. These are constraints that we prefer to satisfy, but can relax when necessary, such as velocity bound. We also maintain a skill library that contains primitive skills for different tasks. They may also come in different forms. For example, we have parameterized skills such as skewering for feeding, and learning-based skills such as VLA policy for cutting. Our high-level task planner will first generate a sequence of skills. Each skill is then passed into a control barrier function, which uses constraint to get certified safe robot actions. Let's dive deeper onto real-world scenarios. For example, in a social dining scenario, the robot avoids blocking the user's view of the TV and other guests during feeding. When human approaches the robot also backs off to maintain a safe distance to avoid violating safety constraints. Let's take a deeper look at the collaborative meal preparation scenario. When the robot is with a parallel gripper, if a person gets too close, the robot backs off to maintain a safe distance. But when the robot needs to perform a different task, let's say cutting task, it will grasp a knife. When the robot is holding the knife, the safety concern changes. Now, when the human approach, the robot not only backs off, but also rotates its end effector so the knife points away from the human. We evaluate our framework in simulation across various environments and robots on 4 different daily tasks. Overall, we achieve 80% task success rate and about 90% constraint satisfaction rate. We further validate our system through real-world user studies on 2 tasks, feeding and meal preparation, using 2 different robots, Kinova and Franca. Compared with baseline methods, our approach leads to higher user perceived safety and greater user satisfaction. Please come to our post session and scan the QR code to learn more information. Thanks.
Our next presentation is Beyond Failure Recovery, an engagement-aware human-in-the-loop framework for robotic systems. And our presenter is Jiaying Feng.
Hi everyone, we present our work from Ampress Lab, EMPC, a human-in-the-loop framework for robotic systems that prioritizes user engagement in physical human-robot interactions. EMPC enables robots to reason about when and how to involve users, improving interaction satisfaction. Conventional human-in-the-loop approaches typically involve users only when a robot encounters failure or uncertainty. For example, when the robot doesn't know which object to pick up, it will ask the user for help. But in physical HRI, in addition to task success, human factors also matter a lot. For example, in an assisted feeding task, the user may want to get involved in robot's decision-making process. However, by following the conventional human-in-the-loop methods, the robot doesn't ask the user because it knows how to complete the task. Over time, this can lead to user dissatisfaction and lower continued use of the system, even when the task is completed successfully. This motivates our work, a framework that considers human factors in addition to task completion when deciding when and how to involve users. We mainly consider 2 human factors, user engagement and user workload. In our EMPC framework, the user first specifies their desired engagement level and the maximum workload they can accept in this task. During task execution, the robot can interact with the user by asking queries selected from a set of questions. These queries vary in both query difficulty and query response difficulty. Queries can be questions that can directly help the skill execution, like the question here, asking user to draw the skewering point. Queries can also be task-related questions, but they do not actually help skill execution. They are only intended to increase user engagement, like the question here, asking the shape of the food item. The interaction dynamics model predicts future engagement level according to related query properties and history. Similarly, the user workload model predicts future workload using query properties and history. Together with the scale confidence from robot's autonomous policy and the user-specified desired engagement level and workload threshold, EMPC chooses interaction actions that balance user experience and task performance under different possible prediction scenarios. Now let's look at some example scenarios. Here's the setup we used in the demonstration and the user study. A robot performs the byte acquisition part of robot-assisted feeding with a user with emulated mobility limitation. In one example scenario, the prediction indicates that not querying the user would cause engagement to fall well below the target level. In conventional human-in-the-loop systems, the robot simply won't query the user because the scale confidence now is high. But in our EMPC framework, it chooses to issue a query to increase user engagement. In a different scenario, if the prediction shows that querying the user would make their engagement level around target, but would also cause user workload to be too high, EMPC prioritizes maintaining bounded workload and chooses to not query the user. In another scenario, the prediction indicates that if the robot asks the user the join-based question, the engagement would be around target, but the workload would be too high. EMPC then decides to ask the non-actionable query, which does not help scale execution, but helps boost user engagement. The non-actionable query has a lower workload demand, so asking it does not violate the workload limit. We conducted a user study with 10 participants with emulated mobility limitations. The user study results suggest that EMPC delivers user engagement-aware interactions while keeping bounded user workload and task success. Thank you for your attention. To know more, please check out our poster and visit our website.
Our next presentation will be on knowing when not to help, active estimation of human reachability for just right robot assistance. And the paper will be presented by Joyce Yang on behalf of the authors.
Good morning, everyone. I'm Joyce, and I'll be presenting Knowing When Not to Help, Active Estimation of Human Reachability for Just Right Robot Assistance on behalf of my lab mates at Emprise Lab. So for users with mobility limitations, more help is not always better. Consider this sandwich-making task. Some objects are reachable and some are not, and the robot needs to decide when to help. Now, if the robot over-assists, it may move an object close to the user even when the user could have reached it, and this completes the task, but it can reduce physical engagement and take away opportunities for the user to utilize the remaining functional capabilities. Now, on the other hand, if the robot under-assists, it may place an object too far away, or fail to intervene when the user cannot reach it. And this could lead to task failure, frustration, or even unsafe effort. So the key insight is that assistance needs to be calibrated to the user's ability. And this motivates our framework, a clinically and biomechanically grounded approach for just right robot assistance. At a high level, our framework has 4 components. First, the clinical grounding module takes a user profile with information such as medical condition and functional description in natural language. Then, we use GPT-4o together with GraphRag over a database of 5 million rehabilitation literature records. The system retrieves clinically relevant evidence and uses an occupational therapy-informed reasoning process to estimate reachability bounds. The output provides clinically grounded estimation of per-joint reachability in degrees. However, an LLM is not enough. They may produce condition-level reachability estimates and are not personalized. So to address this, our framework further uses a latent reachability representation to support active learning for estimating user-specific reachability. First, we synthesize reachability parameter profiles and learn a latent embedding for each profile using an autodecoder. Also, we regularize the latent space in 3 ways. Geometric regularization places similar joint space reachability shapes close together. Clinical anchors from the LLM pipeline encourage profiles with similar clinical conditions to be nearby. And biomechanical anchors from musculoskeletal simulations further ground the space in physiological mechanisms. After this offline training, we used the learned latent space for online active estimation. We first transformed the LLM-derived joint space reachability into a latent initial belief. Then, we actively select informative reachability queries using entropy-based acquisition. After each query, the user either succeeds or fails, and the robot updates its posterior over the latent space. Over multiple steps, the posterior becomes more accurate, and the decoder converts it into a joint space reachability estimation. For example, this video shows how the active learning module infers user-specific joint space reachability through queries. Finally, this reachability estimate is used to modulate robot assistance. If the target is reachable, the robot should avoid unnecessary intervention. And if the target is unreachable, the robot should place objects at a just right location. Also, with this adapted ARAT task, which is a clinical test of upper limb function, if the user's reachability changes after the initial active learning calibration, our framework supports online updates through additional queries. Finally, a real robot user study with 10 participants under emulated mobility limitations showed that our just right policy improved physical engagement without compromising task success. Please visit our website for more information and see you at our poster session. Thank you.
And our final paper in this session is a minimal deterministic approach to shared control for safe powered wheelchair driving, presented by Kyle Puckett.
Good morning, everyone. My name is Kyle Pulkit, and today I'll be presenting our work titled A Minimal Deterministic Approach to Shared Control for Safe Powered Wheelchair Driving. Powered wheelchairs create access to independent mobility, but they pose significant operational challenges and safety concerns. Visual, motor, or cognitive impairments may also prevent individuals from safely operating a powered wheelchair independently, so robotic wheelchairs with driver assistance have the potential to mitigate these issues. These driver assistance systems often use shared control, but common blended arbitration schemes can deadlock or behave unpredictably when intent inference is ambiguous. Prediction-based approaches also make assumptions that often do not hold across varied users, tasks, and operating conditions. These challenges have limited the real-world deployment of these smart wheelchair systems. Instead, we opt for minimal deterministic intervention built on a commercially available smart wheelchair system. There are currently 2 smart wheelchair systems on the market, and we build ours on Lucy. We choose this to ground our shared control algorithm in real market-ready hardware, ensuring our approach is constrained by and compatible with deployment conditions. Now, Lucy assists users by thresholding the user's driving control input based on obstacle distance in these environmental zones, and then it calculates speed thresholds and assigns them to corresponding user input zones. On top of this, we build React, our minimal shared control paradigm. React takes action only when safety constraints are violated, operating deterministically on the instantaneous user command, and they select an alternate control action only when needed. So as a result, React is task agnostic, it's responsible to changes in user input, and it's robust to user, environment, and task variability. Now, let's briefly walk through this React algorithm. First, we get the safety threshold of the current command based on the Lucy zone thresholds. Then, we determine whether React should activate. There are 2 conditions in which React will activate. The first is that the current command must be unsafe, and the second is that it will be sufficiently throttled by Lucy's safety computations. If these conditions are met, then React takes action. From here, we sample alternate command headings within a cone centered on the current user input vector. We then generate can't commands from the sampled headings and zone safety thresholds. And the yellow dots here are the can't commands for React. Finally, we score each of the candidates based on safety and alignment with the original user inputs. So here we have a video of React on an elevated sidewalk, and we see that as we approach the edge, React actually redirects the user away from the drop-off. Overall, React aims to preserve general directional intent of the user, but also preserving motion towards a safer region of the control space. To evaluate this, we've developed a 5-session longitudinal user study protocol that spans 2.5 weeks and allows us to compare user interaction across different assistance paradigms with shuffled task and condition orderings. Clinicians are also present that are evaluating and scoring participants' wheelchair driving capacities for each task. We present 4 case studies with powered wheelchair users across varying diagnoses and control interfaces, and we try to match each participant's own interface as closely as possible on our study wheelchair. For clinician scored capacity, P1 is a skilled driver at baseline, and they saw no notable changes in capacity scoring, while P2 saw notable improvement under the Lucy and React condition. P3 saw an approximate 30% increase in their capacity scoring across both assistance types. We also report safety-related metrics, and the different assistance conditions change the percent of safe trials and the number of safety incidents counts differently across participants. For example, P3, who has vision and hearing impairments, found Lucy and React to be less useful than just Lucy because of its redirective nature. In summary, we introduced React, our lightweight, minimal intervention, safety-driven shared control algorithm for powered wheelchairs, our longitudinal evaluation protocol consisting of many driving tasks, and we present results from our user case studies. To find out more, to chat more about this, please speak with me at our poster after this. Thank you for your time.
I will now ask all of our speakers to come up to the stage, and I'll ask the audience to please come to the aisle microphones and ask questions.
Hi, for the cool paper that had like Yoda as a robot, I forget the name of the title. Yeah, there you go. I was wondering how you handled the head prosodic motion. So like you had a transformer so that mapped from audio to the blend shape motion. How did you handle like the head moving around as well? Like, did you use a data set or model it? I'm interested in that.
Yeah, our data set containing the head motions, but the head motion doesn't use the mapping network from the blend shape coefficients to the actuator, but we use because we construct the neck structure, so I know the inverse kinematics of neck. So if you give me 3 Euler angles from the head motion, so I can target it to the real neck motion.
I think we have somebody by the mic here. Yeah, please go ahead.
Sure. For the EMPC engagement aware paper, how are you quantifying workload and engagement? Is it like questions per task, questions per second? Is there some other metric of complexity of the interaction?
Yeah, in EMPC, we consider the query properties. So we're not considering like other factors. So kind of simplified a little bit to only consider the robot-induced engagement and workload. So in our paper, it's basically different types of queries, and if the robot queries the user at a certain time step. So query frequency and query properties. Yeah.
Thank you.
Okay, we have a question in the far corner with the orange cube.
How's it going? For the embodied to environment paper. Yep, so my question is regarding the experiment with the knife. I'm curious, how hard was it to get it approved? And there was some success and failures, and could you describe a bit about what the failure modes were with regards to that experiment?
So just to clarify, you want to ask the failures about the knife experiment?
So 2 questions. So in terms of like the approval process, can you talk about a bit more about that? And then the second question is the failure modes of that experiment.
I think for the failure modes, the main failure modes I think is sometimes the perception error, and the policy is not always accurate, and it might have some weird option. But fortunately, we have many safety guarantees in the safety device to ensure that the disaster failure doesn't happen. Like we have an emergency button for the user and also for the experiment.
Thank you.
So the first question was around ethics approval. What was the procedure for getting approved to run those user studies?
You need to have an IRB, and you need to tell users the exact process, and they need to sign a consent form, basically.
But yeah, the IRB was tough. It was not easy. But
We have one question right here.
Yes, this is for the robots that know what to ask. Thank you very much for your presentation, very interesting. I was wondering, so the robot asks clarification questions with natural language, and then the user has to provide additional demonstrations. Would it be possible for the user to also provide an answer with natural language and just use natural language to correct the weights, or is it necessary to provide more demonstrations all the time?
So for the current paper, it's just more demonstrations because we combine the 2 demonstration sets together and learn one final reward function. But in future work, we would love to also include other forms of communication from the user and feedback.
Okay, thank you.
Do we have any other audience questions? Okay, if some of you are too shy to ask questions in front of the whole auditorium, please go to the poster session and chat with all our presenters during the poster session. Please join me in thanking them all today.
Hello again. Thanks, everyone. It's my pleasure again to introduce one of our sponsors of RSS 2026. Especially delighted to welcome Toyota Research Institute back. So they've been supporting RSS for the past few years, and we are very grateful for your support. Please join me in welcoming Dr. Masha Itkina. She's the research lead and manager at TRI. And Masha, the stage is yours.
Thanks a lot. Hi, everyone. Almost lunchtime, I promise. So, like Payman said, I'm Masha Itkina. I'm a research lead and manager at Toyota Research Institute, or TRI. We'll start with talking about how TRI works on autonomy that amplifies humans, and we have a short video to give you a sense of the work that we're up to. Awesome. So TRI was established in January 2016. We actually turned 10 years old this year. Our purpose is creating Toyota's future capabilities. We're thinking about research problems that are 20 to 50 years out. We're also really focused on amplifying human ability with the technology that comes out of the research that we do. We're a mid-sized company of around 350 employees. We have an office in the Bay Area in California, and we also have an office in Cambridge, Massachusetts. One of our important attributes is our university program. It's fairly diverse and quite large. It spans across North American institutions, and we have 6 papers here at RSS that are a result of our collaboration, so between TRI and the university partners. We have 5 divisions as part of TRI. This includes automated driving and advanced development, energy and materials, human-centered AI, human interactive driving, and robotics. I'm going to briefly overview 3 of these divisions that are most focused on embodied intelligence. So first up, the Human Interactive Driving Division works to accelerate the path to intelligent vehicles that place the human at the center of a more evocative and safer driving experience by considering control at the physical limits of the vehicle. Then we have the Automated Driving Advanced Development Division, which is pursuing safe, scalable, automated driving technology, enabling mobility for all. And finally, while it's loading, we have the Robotics Division, which is developing human amplification robotic capabilities and tools to address socioeconomic challenges of aging society, labor shortage, and sustainable production. This includes developing and understanding the world's most capable robot foundation models to enable general-purpose robots that improve the quality of life for all people. These are some of the things that we're interested in as part of full-stack learning-based autonomy. We care about data. This means collection, curation, the sources of the data. We think about policy, both from a pre-training and post-training perspective. policy evaluation, robustness, world modeling, upon deployment, adaptation and continual learning, and finally, robot learning with human interaction. This is just a set of a few of the topics that we care about. There are many more. Zooming into a couple of these, we've had some recent releases that I'd like to highlight. On the data collection side, we have Raiden. This is an open source data collection toolkit that uses bimanual YAM robot arms. There is automated calibration. You can teleop the demos through space mice or leader follower arms. We then have our policy learning release called VLA Foundry. This is an open source training framework that allows you to have full control over the components of a VLA. That includes the LLM, the VLM, and the action head. And the idea is these should be easily swappable so you can test different architecture choices. On the world modeling side, one of the releases has been AnyView. And the idea there is you can predict a novel viewpoint for a video, which could be an autonomous driving video, a manipulation video, or any general video. And finally, we have a blog post that came out on rigorous policy evaluation. And there we care not only about a statistically rigorous policy comparison framework, but also one that is highly efficient, particularly since on-robot evaluation is so very human time intensive and expensive. This is a list of the 6 papers that we have here at RSS. A lot of the researchers are also here at the conference, so if you'd like to learn more about the papers, come by the TRI booth to chat with them. And with that, thank you. You can also learn more about TRI and our open positions online.
We move straight to the manipulation technical session. Thank you.
All right. Thanks, everybody. I'm Nico Sinderhoff. I'm with the Queensland University of Technology, and it's my pleasure to co-chair this session, the 3rd session on manipulation, together with Rudolf for the next few minutes. So you know the drill. All the authors should be ready to speak. And our first paper is R2RGen, real-to-real 3D data generation for spatially generalized robotic manipulation, and it's going to be presented by Ang-Yuan Ma.
Hi everyone. We present real-to-real 3D data generation for spatially generalized manipulation that generates data from single human demonstration. Spatial generalization is a data problem. A policy only works where its demonstrations were collected, so covering a workspace takes hundreds. Existing data generation methods have limits. Simulation methods like mimicgen suffer from symmetrical gap. Demogen edits real data, but only for a fixed camera and a single object. In contrast, our method works entirely in real domain. From a single demonstration, it generates hundreds of spatially diverse ones with no simulator or rendering. The core idea is to edit the demonstration as a 3D scene. This keeps the data real, supports multiple interacting objects, and works across different robots and cameras. Well, in the first stage, we prepare the demonstration. We separate the scene into objects, background, and arm, and complete each object's occluded parts. We then divide the trajectory into skills. Annotation only takes under a minute per demonstration. The second stage is the core. From one demonstration, it produces hundreds of new ones. Each object moves with the motion acting on it, and the connecting motions are replanned. We can also shift the robot space giving new viewpoints and mobile manipulation. Edits are applied in inverse order, so later changes never break earlier ones. Finally, in the third stage, we make the point cloud match a real depth camera. We remove points the sensor could not see and fill the remaining gaps. Next is the full pipeline. From one demonstration, our method generates a diverse data set. We train policy and deploy it. The same task success as the object position and camera viewpoint change, all from that single demonstration. Our method also supports mobile manipulation. A mobile robot cannot stop at the same position, so its camera observes a different viewpoint each time. Because space augmentation already covers these viewpoints, the policy remains reliable with little real data. In experiments, a policy trained on data from a single demonstration performs comparably to 25 human demonstrations and far better than that demonstration alone. The method also extends to deformable and articulated objects, such as a box or cloud, using a shape compression model like SAM3D. The method also scales well. Adding more generated demonstrations improves performance until it saturates, and adding a few more source demonstrations raises the overall performance ceiling. Spatial generalization also helps with appearance. On a board placing task with 4 appearances, our method matches the baseline using 1 real demonstration per appearance instead of 10 for less data. To summarize, our method achieves spatial generalization from a single demonstration. It is real to real, requires no simulator or rendering, and generalizes across different robots, new objects, and new appearances. Our paper code and videos are on the paper website. Thanks for your attention.
Thank you, Ang Yang. Next up is Yuliang Wu presenting DEX Grasp Zero, a morphology-aligned policy for zero-shot cross-embodiment dexterous grasping.
Hello, everyone. I'm Yuliang. Today, I'm excited to present our DEX Grasp Zero, a morphology-aligned policy for zero-shot cross-embodiment dexterous grasping. Okay, to meet the demand of increasingly diverse dexterous hand hardware, it is crucial to develop a policy that enables zero-shot cross-embodiment grasping without redundant relearning. However, current IO policy often struggle when transferring skills and thin hands. We identified 2 major bottlenecks in existing IOL methods. First, topology misalignment. Relying on public templates such as model or shadow create artificial structural mismatch. This degrades alignment physical perception. Second, physical constraint violation. Retarget from mediate motion, target live fingertip position, or template often violate the specific kinematic limit of the target hand. So we think, can we design a representation that aligns perception across all hands without simplified modeling, and can enable end-to-end inference to bypass retargeting? So our answer is DEX Graph Zero. Our first design is the morphology-aligned state and action space. We propose an anatomical state graph. Instead of using rigid template, our graph structure strictly aligned with the physical hand topology. Combined with a motion primitive-based unified action space, our method directly maps the graph representation to visible and physical consistent actions. Based on this representation, we use a GCN backbone to achieve end-to-end co-training across different hands. Compared to prior paradigms, our approach has 3 key advantages. First, it enables unified end-to-end inference. Second, it direct mapping completely eliminate retargeting errors. And third, our representation is topology preserving, which strictly avoid no discarding or zero padding. So here's our pipeline. First, we encode hand object state into graph and global feature. The graph feature and then processed by a GCN to get the node embeddings. To prevent the wrist from being overwhelmed by hand-specific variation, we decoupled encoding. The wrist and finger joint are decoded by a separate head to generate the final actions. This design enables end-to-end co-training without retargeting. But is it enough? While this solves the co-training issue, how can the model perceive the physical difference between hands? To answer this, we propose the physical property injection model. This model injects physical priors such as link length and joint limit directly into the graph feature. This ensures the policy strictly respects a unique physical constraint of each hand. And under this design, we train our policy by PBO on 4 hands and evaluate it on 2 unseen hands in simulation. Our experiment shows that training simultaneously on 4 hands, our method significantly outperformed Parasota baseline by 59% improvement in success rate. Finally, we deploy this unified model onto 3 unseen real-world robotic platforms. As you can see in the video, the robot is continuously grasping on 10 unseen objects. This proves the strong zero-shot generalization capability of this graph zero. In conclusion, this graph zero bridges the gap between different robot morphology. Look ahead. Our scalability design is not limited to rigid hand. It can be extended to soft robot or simple gripper by appending those to the graph. Thank you. Looking forward to see you in the poster session.
Thank you, Yuliang. The next paper is Minimalist Compliance Control, presented by Tyler Lam.
Hi, everyone. This is Minimalist Compliance Control. Contact-rich tasks need compliance, but compliance usually demands force torque sensors or torque-controlled motors that most robots lack. We get it from the motor signals directly on board. So why do we need compliance? With pure position control, contact fails in 2 ways. Too little force, and the end effector loses contact and the task fails. Too much force, and friction grows and tracking degrades. Compliance keeps the robot in stable contact. Here's our approach in action. Toddlerbot drawing on a whiteboard. The end effector holds stable contact from start to finish and adapts to the surface as it traces the shape. The key point here is that there is no force sensor here and no learning in the compliance layer. So how does this work? Existing methods fall into 2 camps. Classical model-based control, which is principled but needs force torque sensors or joint torque control, and it's hard to tune. Learning-based RL compliance policies face the sim-to-real gap and can produce large spikes in forces. We want cheap, reliable compliance. Our method has 2 parts. First, wrench estimation. We read motor current and even the raw PWM signal, and apply a torque model plus the Jacobian to recover the external wrench. No force sensor, no current control, no learning. Second, that wrench drives a spring mass damper that updates the position reference. Plug and play under any planner. This is wiping on Toddlerbot. It wipes the first mark, moves over, and wipes again. Throughout, the compliance layer keeps the end effector in stable contact and adapts to the curved and uneven surface of the VOS as it cleans. How good is the wrench estimate without a sensor compared to the ground truth sensor? Mean absolute error is about 0.7 newtons on Toddlerbot and 1 newton on ARX arm. Compliance does not need perfect magnitude. Only the right direction and frequency band accuracy is enough. Next, imitation learning. We train a diffusion policy with 200 demonstrations on an egg placing task, and with our controller underneath, success rate is 80% versus 40% for position control, which cannot stabilize, contact, or push too hard. Third, a model-based policy for in-hand ball rotation. Ours reaches 21 degrees on average, while position control slips or only manages 2 to 3 degrees. The same method transfers to a very different embodiment, the leap hand, doing multi-finger drawing and wiping. Same motor current signals, same model, same controller, no retraining. Each finger keeps its own compliant contact with the surface and adapts as it moves. The position control baseline either loses contact or presses so hard that tracking falls apart. The approach scales from arms down to dexterous hands. Because the method only needs motor signals, it generalizes across robots easily. Here it runs on the Unitree G1 with no hardware changes, the same controller on a completely different embodiment. That is a plug-and-play embodiment-agnostic property we have here. Any robot whose motor exposes current or PWM can become compliant. Finally, a head-to-head on the drawing task against two state-of-the-art RL compliance baselines, UniFP and Facet. Both struggle to track the path while keeping the right contact force. Ours has the lowest position and orientation error. Minimalist compliance from signals you already have. Thank you.
Thank you, Tyler. Next up is Zhenyu Wei presenting One Hand to Rule Them All, Canonical Representations for Unified Dexterous Manipulation.
Hi everyone, I'm Zhenyu Wei from UNC Chapel Hill, and today it's a great honor of me to present One Hand to Rule Them All. Dexterous hands are highly diverse. They differ in finger numbers, degrees of freedom, kinematic design, and action space. And this makes it hard to train one policy that works across different hands. So for cross-embodiment learning, we need two things. First, a unified action representation that is compact, expressive, learnable, and interpretable. And second, a unified action space with the same dimension and consistent joint semantics across hands. Existing representations are not ideal. URDFs contain full kinematic information, but are hierarchical and heterogeneous. Meshes or point clouds are network-friendly, but mostly static and lack joint structure. So what we need is a network-friendly representation that still preserves the morphology and kinematics. Our solution is a canonical URDF. We define a hand template with up to 5 fingers and 22 dots. Missing joints are simply deactivated. And we also use capsule links and unified coordinate frames to standardize both morphology and joint semantics. From the original URDF, we automatically parse the canonical hand parameters and generate a standardized canonical URDF. And at the same time, we maintain a bidirectional mapping between the original and the canonical action spaces. And here are examples across different robot hands. The canonical models preserve the main hand structure while putting all hands into the same format. For experiments, first, we test whether this representation is learnable. A VAE learns a continuous latent space of hand geometry and kinematics. An interpolation produces smooth transition between different hands. And second, we evaluate physical fidelity. In dexterous grasping and in-hand reorientation, the canonical URDF achieves behavior close to the original models. And we then train one grasping policy across Allegro, Barrett, and shadow hand. Conditioned on the canonical representation, the same policy achieves high success rates across all 3 hands. To test zero-shot generalization, we generate more than 100 leap hand variants by changing the finger structures and train a unified policy over these morphologies. The results show 2 things. First, the policy still performs well on unseen hand morphologies. And second, when given the wrong hand conditions, performance drops significantly, showing that the model truly uses the morphology information. And finally, we deploy the policy on the real hardware. Across different leap hand variants and daily objects, the robot achieves robust grasping and includes zero-shot variants without additional fine-tuning. And here are the real-world demos of showing the representative grasps on different objects using the original leap hand and the reduced morphology variants. And here we further test more hand variants and showing that the same framework can handle substantially different finger configurations. And in summary, Aura provides a canonical parameter space, a canonical URDF, and a unified action space for the scalable cross-embodiment dexterous manipulation. And feel free to talk to me at the poster section and visit our website for more information. And thank you for your listening.
Thanks, Jen Yu. Our next paper, paper number 5 in this session, is Access Guide, Grounding Robot Action Coordinate Systems in RGB Observations for Robust Visuomotor Policies, and presented by Jiyun Jiang.
Okay. Hello, everyone. I'm Jiyun Jiang from Korean University. Today, I'd like to present our work, Access Guide, Grounded Robot Action Coordinate System in RGB Observations for Robust Visuomotor Manipulation. This is a joint work with collaborators from University of Michigan and Korea Telecom and Kakao Mobility. Let's go start. Recent visuomotor policies have achieved impressive performance of many manipulation tasks, but one question we asked is, do today's imitation learning policies actually understand actions? As shown on the left, although the object remains the same, the policy often fails when it appears at unseen locations. On the right, you can see that successful executions are mostly limited to regions covered by the training data, showing poor generalization to novel object locations. Yeah, our hypothesis is that current visuomotor policy do not truly understand the robot action coordinate system. Given only an RGB observation, there are many possible ways to interpret the robot's X, Y, and Z axis, as shown here. Without knowing which coordinate system is correct, the policy has to infer the meaning of its action purely from visual appearance. We believe this ambiguity makes it difficult to generalize to unseen situations. To resolve this ambiguity, we propose Access Guide. The key idea is simple. Instead of asking the policy to infer the robot action coordinate system from RGB images alone, we explicitly visualize it in the image. Using the camera calibration parameters, we project the robot's base frame axis into each camera view, generating what we call Access Guide visual cues. These cues are then concatenated with RGB observation and fed into any visuomotor policy. Then, does Access Guide improve object location generalization? The answer is yes. Compared to the baseline, our method successfully generalized to a much larger region of unseen object locations. Yeah, here are some qualitative results. In all of these results, the object is placed in novel locations that were never seen during training. Using the same experimental setup, we observed consistent trends in real-world evaluations. Finally, here are the quantitative results. These results show that explicitly grounded robot action coordinate system consistently improves generalization in both simulation and real-world manipulation. Yeah. Finally, let's look at real-world qualitative results. Although the object is placed at unseen locations, the baseline fails to reach the object, while Access Guide consistently succeeds by correctly grounding the action directions. We also report the results on better simulation environment. On average, our method improves task success by over 8% point compared to the vanilla model. Yeah, here are some sample rollouts from each task. Yeah, here are some sample rollouts for each task. Using small VLA as our baseline, we also report improved results for each libero suit. Next, we investigate whether Access Guide also improves viewpoint generalization. During training, we use demonstrations collected from multiple camera viewpoints, and during evaluation, we test the policy under unseen viewpoint. Yeah, here are the quantitative results. Across our viewpoint, Access Guide achieves the highest average success rate, and these results show that Access Guide also improves robust to viewpoint changes. And we have more experiments. Please come by our poster if you have any questions. Thank you for your attention.
Thank you. Next up, we have Learning the Formable Object Manipulation Using Task-Level Iterative Learning Control, presented by Krishna Suresh.
This is a flying overhand knot. In this work, we learn a flying knot from a single demonstration and less than 10 trials. There we go. When we try to get the robot to track the human demonstration directly, it unfortunately fails at the task, since the robot has different morphology and velocity limits than the demonstrator. So let's try to make the robot learn to tie a flying knot. if we can measure some task errors from each failed attempt and map that to command corrections and iteratively improve our command over trials, then hopefully we can converge to a successful command. And since we're improving a feed-forward open-loop command over trials, we can use a method called iterative learning control, which is a data-efficient learning method often used for precise trajectory tracking. ILC starts with an initial command and then maps that through the real system to get some task state, and then maps errors from this task state through an inverse model to get some command correction. This inverse model here is really the key piece of ILC, which allows for efficiently updating a command by using approximate gradient information from a model. ILC still works really well when using an imperfect model. So we can simplify the dynamics of our system by treating the robot as a kinematic object and modeling the rope as a serial chain of only 11 point masses. Now that we have a way to improve our command, let's do some learning. And more specifically, we're learning to match the rope motion from the entire demonstration. You can see before learning, the rope tracking is much worse, and after learning, the rope tracking improves much better, but we still fail to tie a flying knot. So if we take a step back and look at how instructional materials teach a flying knot, the instructor often points out this collision point as a really important part of the task, and I'll refer to this as a critical point. And in general, critical points are just any part of the task that has high spatial or temporal importance to the overall task success. So if this is an important part of the task, what if we just ignore everything else and only reduce errors at the critical point? And that's exactly what we do. And you can see, within 5 trials, the robot succeeds at the flying knot. And you can see right at the critical point, the robot matches the demonstration well enough that with the follow-through motion, the robot succeeds at the task. Here's a comparison of the final learned command with each type of objective. And you can see, with the critical point objective, we're actually sacrificing performance at the unimportant parts of the task to achieve high performance right at the critical point. We then evaluate how well ILC can learn the task on different rope dynamics. And it's able to successfully learn on the real system with different types of ropes, like a chain and latex tubing. And we also test to see how well ILC can learn a flying knot with different types of demonstrations. And once learning succeeds, the robot is effectively 100% successful with 0 failures over 40 repeated trials. And finally, I'll go over a few high-level takeaways. Attention is all you need. Maybe not this type of attention, but task-level attention to the right parts of the task enable sacrificing performance of the insignificant parts of the task to achieve high performance. ILC enables fast learning by effectively performing trajectory optimization on the real system, but using gradient information from a model. And repeatable goals enable a task to be ILC-able from a resettable initial condition, and critical points can come from instruction or search more broadly. Thank you all for your time and attention, and come try out a flying knot at the poster session.
Thank you, Krishna. Next we have CLAMP, Contrastive Learning for 3D Multi-View Action-Conditioned Robotic Manipulation Pre-Training, presented by Connor Schenk.
Thank you. Yes, I'm Connor. I'll be presenting CLAMP. This is work done by my student researcher, Arthur, who unfortunately couldn't make it, so I will be presenting on his behalf. So recent work on contrastive pre-training has used web-scale image-text pairs to train strong vision encoder backbones, for example, CLIP. Currently, there's no analogous paradigm yet in robotics due to the scarcity of large-scale robot data. So we looked at what makes good pre-training data for robotic manipulation. We looked at how robots perceive the world, and how robots act in the world. And that gave us the idea for CLAMP, which is a 3D multi-view action-conditioned pre-training framework for robotic manipulation. We could trustfully pre-train an image encoder, a text encoder, and an action encoder on large-scale simulated robot data. Specifically, we learn a model psi that generates image and action embeddings that can be utilized by a downstream behavior cloning policy. Given image, text, and action triplets, our contrast objective pulls the embeddings of matched triplets closer together while pushing apart the embeddings of mismatched triplets to better cover the space. We then fine-tune a policy on top of this from expert demonstrations using our frozen image and action embeddings. The input to our image encoder is actually a point cloud that we then render onto 5 virtual cameras, 3 of which are fixed in space, and the other 2 are attached to the robot's end effectors. We found this provides clear observations for high-precision manipulation tasks. Furthermore, we use string to help make the attention mechanism aware of where things are in 3D space. String enables tokens from different views to be properly correlated if they look at the same spot in 3D space. Specifically, we use the Cayley string variant. Our action representation is a pretty standard action encoder transformer. And our text representation, we borrow the text tower from Clip. Here are some very scary looking equations. These are just the SIGLIP contrastive training loss taken between each pair of action, text, and image encoders. We also found that it helps quite a bit to pre-train our diffusion policy on both sim and real data. We found that this appropriate initialization substantially improves fine-tuning efficiency and performance. And finally, we fine-tune a task-specific diffusion policy. We adapt our framework from the Aloha Unleashed paper. Here we're adding in our frozen image and action towers. And here you can see our results in simulation. Our method is in green, and you can see that it both converges faster and has higher overall performance than the baseline models. And you can see here a nice table of results in simulation. Again, ours variant here is in the bottom rows, and you can see that we significantly outperform the baselines. In particular, if you look at the third column, the pen and container task, we significantly improve performance over the baseline by quite a wide margin. And here are results on real-world experiments comparing vanilla Aloha Unleashed versus Aloha Unleashed with CLAMP. You can see in 4 out of 5 tasks, we outperform the baseline, and in 3 of those tasks, actually, we outperform the baseline by quite a wide margin. And of course, videos are great. We all love videos. So here are some videos of our actual policy on both the real robot, which you can see on the left, and in simulation, which you can see on the right and on the bottom. And you can see our policy is able to put dishes in racks, to pick up pens, to open and close drawers, all quite well. If you would like to learn more about this, here's a QR code which will take you to our website, or you can come talk to me at the poster session. Thank you.
Thank you, Connor. So next we have Force Policy, Learning Hybrid Force Position Control Policy under Interaction Frame for Contact-Rich Manipulation, presented by Hongjie Fan.
Okay, hello everyone, I'm Hongjie Fan. Today I'm representing our paper, Force Policy. In this work, we introduced a hybrid force position control policy for contact-rich manipulation. Consider the task of plugging in a charger. First, you use vision for global guidance to approach and align it. After contact, you rely on feel to decide where to push and where to stay compliant. During this process, you use force feedback to correct the structure and guide it in. Inspired by this, our force policy uses a global vision policy for guidance in free space and a high-frequency local force policy to regulate the interaction during contact. So, how do we actually define this interaction structure and recovery from data? The key lies in defining the interaction frame directly at the contact point. We use the local stiffness and task intent to separate constrained and free directions, answering 2 critical questions: where should I push and where should I yield? This universal structure applies everywhere, whether it is polishing, flipping, or tightening a screw. To recover it, we rely on 2 simple rules: subtract friction-like forces in dissipation-heavy phases, and subtract compliance motion in elasticity-heavy phases. After obtaining the interaction frame, we can identify the contact mode and extract the control parameters, which serving as a ground truth. Now, how do we turn this into a global local organization for robot control? Our answer is a global local vision force policy. A global vision policy understands the scene and provides a high-level action and a global context. Then, a high-frequency local force policy takes over for interaction. It produced structure control signals for contact, interaction frame, reference range, and a selection mask, along with the action. These are exactly the structure we defined and recovered previously. And they give us the supervision to train the local policy and predict them. Finally, we use an asynchronous scheduler with a simple router to decide where to stay with the global action or give control to the local policy. So